Welcome. This is a lecture about relativistic cosmology. Well, what is relativistic cosmology about? Relativistic cosmology is the application of Einstein relativity to the universe. So, we want to construct a model of the universe based on Einstein general relativity. For that reason, you are supposed to be familiar with Einstein with the essentials of Einstein general relativity to understand this lecture. In particular, you are supposed to know about the Einstein equations, okay, with cosmological constant, okay, and you are supposed to be familiar with the standard representation of the universe as a Lorentzian manifold. Okay. So, what we are going to explain in this lecture is how to construct a solution of the Einstein equations which represent the universe. This will lead us to the so-called standard cosmological model, also known as the ΛCDM model. Okay, lambda. This lambda is the same lambda which you see here in the equations, and CDM stands for cold dark matter. Well, I will explain the meaning of these terms during the lecture. Now I'm just telling you the model which we will study in this lecture, okay? Right. Okay, so and how are we going to construct the ΛCDM model? How are we going to construct our model of the universe? Well, to do that, I am going to put forward what is known as the basic postulate of cosmology, which is the cosmological principle. Okay. And what does the cosmological principle say? Well, it says the following. Okay. Cosmological principle says that at any time and when looked at large scales, the universe is homogeneous and isotropic. Okay? But, well, what does this statement really mean? Okay, let us just discuss this statement in detail because it's very important. So, What do I mean by at any time? Well, if I say at any time, I have to specify who is measuring the time. Um, this is the time of cosmological observers. These cosmological observers are inertial observers which are those who see the universe homogeneous and isotropic. Okay. Well, and what is the meaning of homogeneous and isotropic in this context? Okay. Mm. Homogeneous means that it doesn't depend on the location, which in this context means that all universe looks the same to all cosmological observers. Okay, so physical laws of the universe are exactly the same. Uh, Physical properties of the universe are actually the same at any point of the universe, and in particular, and this means that uh, there is no distinction between the cosmological observers. Okay, and isotropic means that we always see the same. We always see the same in if we look at any direction. Okay. Okay. So this is the meaning of this is the explanation of the cosmological principle. And now the question now is, okay, but is it really true, this principle? Is the cosmological principle supported by experience? Well, okay. To answer to this question, let me just give a review summary of the structures which have been observed in the universe. Okay, so let us just describe the structures of the universe. And from this description, we will deduce whether the cosmological principle is supported by the experience or not. Okay, so let us start by the smallest. Well, of course, the universe has many structures. We have atoms, we have rocks, we have there are people, and well, there are many things. But well, just it's important to remark that cosmological principle talks about large scales. Okay, so we are not interested in the universe at any scale. We are talking about the universe at large scale. So we have to we have to look at the universe at large scales. How large are these scales? So okay, let us just start by what in cosmological terms is understood as a small scale, and this is the scale of a planet. Okay, so a planet, such as for example the Earth. The Earth has a diameter which is roughly 12,000 kilometers. Okay, this is the Earth. It's a planet, and well. But well, at this scale, if we think of ourselves as cosmological observers and we look at the universe, well, it's clear that the universe is not homogeneous and isotropic. So this is not the scale which the cosmological principle applies to. We have to go to other scale. And well, since we are doing cosmology, we need to go to bigger scales. And for example, we can go to the scale of a star, such as for example our sun. Okay, this is and well the diameter of the sun is a bit bigger than 1 million kilometers, but again at this scale the universe is still not homogeneous and isotropic, because well, it's clear that there are many stars in the universe, but we don't see stars distributed homogeneously in the sky. And well, between stars there are empty, there's space, and it means that the universe is not homogeneous at this scale. So we need to go further, and well, we have the scale of a planetary system with a star in some kind of privileged location, and then planets around it. Okay. Well, we have star and its planets. Well, we now know that there are planets around many stars. Not so long ago, the existence of extrasolar planets was a hypothesis, but now we know that they are quite common. Okay, and if we look, for example, to the solar system has a diameter which is roughly 60 astronomical units. Okay, just remember that 1 astronomical unit is the distance between the Earth and the Sun. Okay, right. So, but well, again, well, this is a big scale, but still, universe doesn't look homogeneous and isotropic and at this scale, because well, we have many planetary systems, but between planetary systems there are no planetary systems. There are other stuff, and so it's clear that at this scale, cosmological principle is not yet true. Okay, so we have to go to a larger scale, and the next thing which we have observed is gas nebulas. Well, gas nebulas which contain gas and material, and which are the source of new planetary systems and stars. Okay, so just going to represent this. So just think of each dot as a gas, hydrogen, helium, or even material. And well, okay, but what interests me now is the scale of these nebulas. And well, they have a diameter which is from 3 to 10 light years. Okay, well, of course, I don't think I need to remind you what a light year is, so I'm just going to remind you. Well, I'm just going to tell you that well, 1 light year is roughly 63,000 astronomical units, just to put us in context. Okay, so it's a very, very big distance, and well, you know that the closest star to the sun, which is Proxima Centauri, is roughly 4 light years away from us. Okay, so this is well, if you compare this number 63,000 with the diameter of our solar system, you realize that this is a very, very big distance. Okay, but well, and then well, a nebula is something very, very big, but still universe is not homogeneous and isotropic at this scale, because well, universe between, if we look at what lies between two nebula, we have star. Well, actually, there we don't know for sure, but there are stars. There are empty. It's just the empty space. So still, universe is not homogeneous at this scale. We have to continue going up in our scale, and well, what we can see if we go up is a star cluster. Okay, so we can see if each of these dots is a star. Okay, we observe that there are groups of stars in certain locations of the universe, which is called star clusters. And again, well, the diameter of one of these clusters is around 100 light years. Okay, so we're still looking, it's something far bigger than a nebula, but still stars are not only grouped in star clusters, but they're even bigger groups of stars, which are galaxies. Okay, galaxies which come in many shapes. Just attempting here to give a representation of a spiral galaxy. Okay, and well, within the galaxy we find these star clusters, and well, there are other kind of structures here which I'm not interested in now, but I'm only interested in the scale of a galaxy, which, for example, the Milky Way is bigger than 100,000 light years. Okay, so it's something which is even bigger than star cluster. But well, if we look if we look at galaxies on this distance, we don't see galaxies distributed homogeneously in the universe. We have to look at a bigger scale, and if we do that, we find that galaxies are distributed also in clusters. Okay, there are also groups of galaxies. Okay, I'm just representing them now. Okay, so just think of each group of dots here as a galaxy, and we have a so-called cluster of galaxies. Okay, and here the distance is something like it's above 1 million light years. Okay, just given some typical distance here. Okay, well, okay, so since we are going up, light year is becoming kind of small unit, and so it's also useful to introduce another unit of distance, which is the parsec, which is it's a bit above 3 light years. Okay, so well, this is something around 10 megaparsecs. Okay, so we but still we see that if we go to higher scales, we will still see structures, and we don't see. If we look at the galaxies at this scale, then we don't see that a pattern, a homogeneous pattern. We see that there still exist bigger clusters of galaxies, which are called super clusters of galaxies. Okay, so just think of each point here as a galaxy, right? And well, we have okay, and this can reach the 1 billion light years. Okay, so well, it's a very it's very big distance, but there's even more if we go to scales which are above 1 billion light years. One sees that galaxies follow a pattern which is a filament. Well, we find that galaxies are grouped in sort of filaments, okay, with voids between them. So I can just think of each of these points as a galaxy. Okay, and here we are looking at something which is bigger than 1 billion light years. Okay, and well, this voids are also well, they're so-called super voids, and well, they are smaller than 1 billion light years. Okay, so we will still see that at these scales, universe is not homogeneous yet, but almost. Well, okay, if we have to go to a scale of bigger than a gigaparsec to start seeing the universe as homogeneous and isotropic. Okay, so I'm just going to represent here a square, which is well, this is the next order of magnitude to which what is the order of magnitude which is both these scales, and and then in this order of magnitude we see the universe as homogeneous and isotropic. Okay, so from this review we conclude that the cosmological principle is true, but the scale which is involved in the cosmological principle is a scale which is bigger than the gigaparsec. And in this sense, the cosmological observers which appear in the cosmological principle have the size of galaxies. Or bigger. Well, actually, strictly speaking, a cosmological observer is something which is bigger than a galaxy. Okay, so the conclusion is that we can consider the cosmological principle as a good as true, as but the universe has to be. We are looking at the universe at a very big scale, which is the scale, which is a scale which involves the gigaparsec. Okay, so that's the point, right? Well, that's the cosmological principle says something about the geometry of the universe, so to speak, but it doesn't say much about the composition of the universe. So we need to know something more about the composition of the universe. Okay? We are going to present now another postulate which says something about the composition of the universe. And this is the Weyl postulate. Okay? Well, the Weyl postulate says that the cosmic observers define a fluid or substratum which is the only contribution to the matter energy of the universe. Of course, when I speak about the matter energy of the universe, I'm really talking about the energy momentum tensor which we need to input in the Einstein equations in order to obtain our cosmological model. But okay, so well, this is something about the composition of the universe. Well, I will explain later how this fits with the cosmological principle, with the isotropy and homogeneousness of the the isotropy and the homogeneity of the universe. I will explain how this fits with the isotropy or homogeneity of the universe. But before that, let me also complete the Weyl postulate with something else in relation to the properties of the cosmological observers. Because, well, this postulate says how the cosmological observers affected to the universe. Because it says that maybe I just write it down and then explain it later. Okay, well, this is a statement about the cosmological observers, and well, each observer has a clock. We can think of that each observer carries a clock, and the thing is that we can use this clock to define a hypersurface in the universe, which are the set of points in which the clock gives the same value, and also, in addition, the world lines of the cosmic observers are orthogonal to this hypersurface. Well, I'm going to discuss the geometric implications of this statement now, but let me just say that relativistic cosmology is based on the cosmological principle and Weyl postulate. Okay, so these are the two main ideas which we will use to construct our cosmological model. Okay, and now, well, let us just extract the information about this geometric property. Okay, so the fact that that we can define a hypersurface with the cosmological observers. Well, let me just let us just take a region of the universe in which cosmological observers don't intersect. Okay, so I'm just drawing in red the word lines of cosmological observers. Okay, so these are and since these lines don't intersect, this is a congruence, so-called congruence of cosmological observers. Okay, right, and well, since well, the first point is that cosmological principle said that cosmological observers are inertial observers, so it means that this is a geodesic congruence. Okay, so these lines which you see here are geodesics, and Weyl principle said that well, the time which well, this cosmic time, well, I forgot to mention that indeed this cosmic time is indeed the proper time of which well, it's not stated here, but since this is the time defined by a cosmological observer, it indeed corresponds to the proper time of each observer. So the cosmological time of this congruence is its proper time. Okay, so so that's it, and well, and since this time defines a hypersurface, what it means is that we can just join those points which in which the proper time is the same, and what we get is a hypersurface. Okay. Well, this is not well, this is not true of any congruence, but in this case we are demanding that property, and when this happens, we say that the congruence is integrable. Okay. Right, so the bottom line is that there is a foliation of the universe by hypersurfaces defined by the proper time of the cosmological observers. Okay, and Weyl principle also said that these lines, which we have here, are orthogonal to the hypersurfaces. Okay, so I can just indicate this with this symbol. Okay. So the conclusion is that we can now construct a coordinate system, which is the so-called co-moving coordinate system, which is defined with the time measured by the cosmic observers, which from now on I will call cosmic time, and coordinates which represent the position of each observer in the hypersurface, in the hypersurface, in each hypersurface of the foliation, which is also known as the comoving hypersurface or comoving hyperplane. Well, different names. Yes. Yes, okay. Okay, so the point is that these coordinates, well, since this is the proper time, well, these coordinates are adapted to the congruence of cosmological observers. Okay, and what this means is that, well, if we denote by U the vector field generated by the congruence, which means that is tangent to each curve of the congruence, then in these adapted coordinates, this looks it adopts this this form. Okay, and well, I will well, we will take this as the unit vector. Well, as the, so if this if G, so if I just adopt this notation for the metric of the universe, then since well, this is the affine parameter of the congruence, then we deduce that this vector has to be normalized. So which means that well, I'm just using, well, this is a Lorentzian metric. I'm just using the convention which is standard in relativity, and this is the signature convention. Okay, of course the observers of the congruence of cosmological observers are well, the congruence, this is a congruence of observers, so these curves are time-like, and it means that this has to be a time-like vector. So that's the reason why this is a negative sign. Okay, right. So, and now the question is, well, can we write down the metric in the comoving coordinates? Well, with this information, we can, or at least we can write part of it. So, in these comoving coordinates, we have that the metric is given by the following expression. Okay. Okay, where here x is an abbreviation for the comoving, well, for the coordinates on. Just remember that this is our coordinates on the cosmic hypersurface, and indeed, well, this we have a minus. Well, the coefficient here is -1 because we have this normalization. Okay, and yeah, and we don't have terms which we don't have dt dx terms because well, the fact that the congruence of observers is orthogonal to this cosmic hypersurface implies that this scalar product is 0 for each value of the comoving coordinate. Okay, so in the end we are just only left with these scalar products, which well, give these values which correspond to this expression here. Okay, so indeed this Sij is just the metric on the hypersurface, on the cosmic hypersurface. Okay, for each value of t. So let me just okay, so we already have some important information about the metric of the universe, but now the point is to find this metric on the cosmic hypersurface. Okay, that's what we have to do, and to do that we are going to use the homogeneity and isotropy, which is stated by the cosmological principle. Okay, and well, in fact, well, cosmological principle speaks about homogeneity and isotropy with respect to the cosmological observers, and what this really means is that this well, this what speaks about homogeneity and isotropy with respect to cosmological observers at a given cosmic time t. Okay, so the translation of that statement is that to be this metric has to be homogeneous and isotropic. Well, what does this mean? What is the real meaning of this? Well, perhaps state in other words, maybe just to this make it more clear that so well, that this comes straight from the cosmological principle, and then from this we get this statement. And well, in how can we formulate this statement in more precise mathematical terms? Well, what this means is that the metric is invariant under translations and rotations on the cosmic plane. Okay, so just remember that the group of translations has three parameters, and the group of rotations has also three parameters. Of course, in a three-dimensional space. Yes, clarify this. As is the case of the cosmic hypersurface. Okay, so this it means that the group of translations and the group of rotations act on the three-dimensional space, on the three-dimensional cosmic hypersurface, and the cosmological principle, or due to the cosmological principle, this metric has to be invariant under the action of these groups. Well, when I speak about the action of these groups on this metric, I'm just saying that. Well, when I say that this metric is invariant under the action of these groups, what I'm saying is that these are isometry groups. This corresponds to these groups correspond to the isometry group of this metric. Okay, so Okay, that's what I am saying. Um, well, just a very brief reminder of if you have well, if you have a manifold and a metric defined on a manifold, then a diffeomorphism of the manifold is an isometry if we have that the metric, the pullback of the metric corresponds to the metric itself. Okay, so this is just the definition of isometry. Okay, and well, yeah, and well, of course, it's clear that the from this definition, it's clear that the set of isometries is a group, which is a subgroup of the diffeomorphism group of the manifold. Okay. Okay. So what we are the thing now is that this property, which comes straight from the cosmological principle, is going to restrict the form which this metric has, and ultimately will give us the form of the complete metric of the space-time. And how does it happen? Well, it happens by means of a mathematical result, which I'm going to state now. And well, this mathematical result was also used in the lecture about the conformal diagram of de Sitter and anti-de Sitter. Well, there's a lecture in which we studied the conformal diagram of de Sitter and anti-de Sitter, and in that lecture I explained a bit about the geometry of de Sitter space-time and anti-de Sitter space-time, and for that I used the same geometric result which I am going to state now, which is the following. So, well, now important result in geometry. So, suppose that we have an n-dimensional pseudo-Riemannian manifold. Okay. Then the result, well, is the following. Okay, I already mentioned that the set of isometries of manifold is a subgroup of the group of diffeomorphisms. Well, we can say even more, and this group is in addition isomorphic to a finite dimensional Lie group. And well, since it's a finite dimensional Lie group, then there is it has a dimension, and the thing is that the greatest possible dimension of this group, which is what I call the maximal dimension in this statement here is this value, where here, well, yeah, it's the dimension. The n is the dimension of the pseudo-Riemannian manifold. And when the maximal dimension is achieved, then it turns out that this pseudo-Riemannian manifold corresponds to a constant sectional curvature space. Okay. 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 Well, I'm going to say something more about these constant sectional curvature spaces, but before doing that, well, let me just explain why we're stating this result now. Well, the reason is that if we go back to our situation, okay, in which we have a metric in a three-dimensional space, which is invariant under an isometry group, which has dimension 6, because we have this three-parameter group and another three-parameter group, okay, which is then well, just this here. Okay, so okay, so that's what we have, and yeah, and okay, and this is a metric on, well, that this is a metric that for each with, well, we know that it depends on t, on the cosmic time. Okay, maybe I just write it in this fashion. The thing is that for each value of t, this is a metric on a free space which has a 6-dimensional isometry group. So and so it turns out that if we look at the formula which gives us the maximal dimension of the isometry group of metric, then it turns out that if n is equal to 3, the dimension of the space is equal to 3, then the formula says that the maximal dimension is just 1/2 3 plus 1, which was just very simple to realize that in this case in this case the maximal dimension is attained. So if we just apply the theorem which I just stated, we deduce that this has to be a constant sectional curvature space, right? So we deduce that for each value of t, we conclude that we have this property. And well, this enables us to write down an expression for this metric in certain coordinates, because, well, there is a second part to this result, which states that for a pseudo-Riemannian manifold, which is of constant sectional curvature, can be written in a certain way in certain coordinate system. So let me just state the second result. Okay, so we have the important thing for us is that the result tells us the form of the metric. So this is the form of the metric, where here this k0 corresponds to the constant sectional curvature, and then well, this eta mu nu is the pseudo-Riemannian Euclidean metric. Okay, so this means that well, if you just compute well, this well, indeed, this well, what this means is that if you just take this part, this is corresponds to the flat pseudo-Riemannian metric. Okay, so these coordinates are still not entirely fixed. What we are demanding is that these coordinates must have the property that when we compute the Riemann tensor of this expression, then it's zero. So this is a flat pseudo-Riemannian metric. And well, okay, and this is the constant sectional curvature. Well, I'm not going to explain in detail what constant sectional curvature means. But well, if you look at the lecture of the conformal diagram of de Sitter and anti-de Sitter, you can find an explanation, a more detailed explanation of this concept there. Okay, but here we don't need that explanation. What we need here is just this expression, and we also need to understand well, that this is a constant and that this numerator here is constructed with a coordinate system on the manifold such that this corresponds to the flat pseudo-Riemannian metric. That's all what we need here. Okay. And okay, so this is a result for an n-dimensional pseudo-Riemannian manifold. So we need to apply this result to our case, which is the case in which the manifold, the pseudo-Riemannian manifold corresponds to this metric. Okay, so we know that this is a constant sectional curvature. So okay, so this result gives us an expression for the metric. So let me just let us just use the theorem now. And well, the theorem says that there are coordinates in which this metric takes the following form. Well, just okay. In our case, the constant curvature can, in principle, depend on the cosmic time t. So I'm just going to write this dependency here. And then we have the Euclidean metric. And here, well, of course, we are going to take the coordinates such that the flat pseudo-Riemannian metric takes its simplest form. Okay, so I'm just going to take well, of course, now since these are space like hypersurfaces, then from it, that implies that this is a Riemannian metric. Okay, so that's why the flat Euclidean metric adopts this form. Okay, so okay, right. So we have been able to narrow down the form of the metrics which we have in each spatial in each cosmic hypersurface. Okay, but the thing is that, well, it's we are going to introduce we are going to change these canonical coordinates, these coordinates which we obtained from the theorem, to another more convenient coordinate system. Okay, so let me just take this expression. Okay, just have this expression here. Okay, well, since in our choice the flat, in this case is the flat Euclidean, the flat three-dimensional Euclidean metric. So this is just square. Okay, so yeah, so this is our expression for the metric in the three in the cosmic hypersurfaces. Okay, I'm just going to write in this form without indices, right? So yeah, so this is the expression we have for the metric, and now, well, just if we do the standard change into if we change the flat Euclidean metric into spherical coordinates, then, well, it's clear that we get the following expression. I'm assuming that you're familiar with this kind of coordinate representations. Sorry, there's a square here missing. I think sorry, I just okay, yeah, sorry, I forgot to well, the theorem says that there is a square here, and that's just that I forgot to add the square in our application. Okay, so there's a square here, sorry, and here. Okay, so we have this transformation. Right, and yeah, so this leads us to this expression for the metric, and then, well, we are going to do a further transformation, which well, is the following one. We are going to transform this the small r with this relation. So here big R is the new coordinate, and, well, okay, you have to write small r in terms of big R and do the replacement here. Well, I'm not going to do that calculation, it's left as an exercise, and if you do that, you find that you can write the metric in this form in terms of big R. and this is the coordinate representation which we are going to use in our application. Okay, so just indicate. Okay, so also I'm not going to for the moment I'm not going to write the cosmic time here t. I'm just we understand that this is there is a dependency here on the cosmic time, but for the moment I'm not going to keep writing this dependency in the formula. I will say when we need to write this dependency. Okay, so this is the expression which we are going to use, and yeah, and the thing is that we can well we can just classify the geometries which are represented by this metric according to the sign of this k-naught, okay, of this, which as I said, for each value of the cosmic time it corresponds to the constant sectional curvature of the hypersurface of the cosmic hypersurface. Okay, but for the moment, well, let's just forget about the cosmic hypersurface, about cosmology, and let us just concentrate on this expression, and let us just study the geometric meaning of this expression. And well, and as I said, we have to the geometries represented by this metric are classified according to the sign of k-naught. So for example, if k-naught is 0, then the metric becomes a very simple form, which you probably recognize immediately as the metric of the Euclidean 3 space written in spherical coordinates. Okay, right. So if k-naught is has positive sign, then well, what we do is that to recognize this geometry, we do a further simple coordinate change. Introduce a new coordinate chi. This is a very simple computation. Okay, and if you do the replacements, you find is what you find is that the metric adopts adopts this form, and this is just the what is the metric in round brackets is just the metric of the 3 sphere. Okay, so in this case, when k-naught is positive, the geometry is the geometry of the 3 sphere. Okay, just remember from well, I also mentioned this in the lecture of well, in the lecture of the conformal diagram about of Minkowski spacetime, and also in the lectures about the sitter and antitheta. But if you don't want to look at that, or you don't remember, just believe me when I say that this is the metric of the three sphere. And in a similar way, if k0 is negative, then well, you do a similar coordinate change, but now you have to change. You have to bear in mind that k0 is negative, and then you have to replace the sign that by the hyperbolic sign. Okay, and then what you get is something which is the following. Okay, and now what this represents is the three-dimensional hyperbolic space. Okay, so you see that this is just, it's very similar. We only have to replace the sign by the hyperbolic sign. Okay. Well, I'm just going to explain a bit the meaning, the geometric meaning of these coordinates. So, in the case of the three sphere, we have, well, let's just draw the here the three sphere, right? And then, well, let us just fix a north pole on the three sphere. Okay, so, and then it turns out that this chi equal to 0 will correspond to the north pole. And well, we can just now draw circles on the three sphere. Okay, well, I have to maybe just try to represent this. Well, okay, maybe using another color, it's better. Okay, so okay, maybe if I just draw this, then we have to do a bit of rescaling. Okay, so okay, so we have all this represents well, these blue curves, which I'm now drawing here, they represent S2 sections on the S3 sphere. Okay, so this is S3, and then this is that's the topology of S2. Okay, let me just put this aside, just because otherwise it's going to be confusing. Okay, so yeah, so this represent, this is S3, this and then this represents S2 sections on the sphere S3. And the thing that is that these S2 sections are parameterized with the theta and phi coordinates. Okay, which are the coordinates which you saw in the previous expression of the metric, and well, and the chi and the chi coordinate parameterizes each of these each of these S2 sections. Okay, so at each of these sections we find that the chi coordinate is constant. Okay, so I'm just going to indicate this with this. And here we have another value for chi. Okay. So yeah, so chi equal to 0 corresponds to North Pole, and then we have that chi equal to p. Chi equal to pi corresponds to the South Pole. So we have that, and then since this is this other theta and phi are parameterizing S2, then we have that these variations. Okay. Okay. So yeah. So this is the geometric description of S3, which is written in these coordinates, and well, we can get a similar description of the hyperbolic of the three hyperbolic space. Okay. So just this. Okay, so I'm just going to try to represent hyperbolic space, right? And now, well, we need to check also a kind of well, here it's not a pole, but it's just a point which we will take as our origin of the chi coordinate. Well, of course, if in the case of the S3, this is North Pole and South Poles are not privileged points. It's just a choice which we make to set the 0 of our chi coordinate, and here we do something similar. We set our 0 of our chi coordinate, but this is not a privileged point. Okay, and also we have here, just copy this. We have here sections which correspond to S2. We have the topology of S2. Okay, this is, I'm just going to draw them now. Here, just another one. Okay, we have this here, this here. Okay. So, okay, so this is a sort of hyperboloid, and then we take sections of the hyperboloid which have the topology of S2. Okay. So it means that they are also parameterized with spherical coordinates. Okay. So I'm just going to write here this to indicate that each S2 is parameterized with theta and phi coordinates, and then, well, at each of these sections the chi coordinate has a constant value. Okay, so I'm just going to here something similar. Okay, and so in this case we see that, well, chi equal to 0 is this point, and then, well, this is a H3 is non-compact, so this is this continues indefinitely, and then this fact is represented by this property. Okay, so we have here that chi varies in an infinite range. Okay, so this is the geometric description of the three cases. The case in which well, k naught is 0, it's just Euclidean 3 space. K naught is positive, corresponds to the 3 sphere, and K naught negative corresponds to the 3 hyperbolic space. And I have just shown in these pictures the geometric representation of each situation. Okay. Yeah. Well. Okay. We will see the application of this to cosmology. But for now, I'm just I have just been talking about geometry, right? Okay, and now let me just do a final simple coordinate change here, which well, let me just take the metric and write it here. Okay. And now, well, the change is a very simple one. It's just a rescaling of big R. Just going to write R in the form, well, where now alpha is a constant. Okay. Well, if we do this rescaling, what we get is just put it here. It's a very simple computation. We get this okay. Where here, well, this is what we get, and here, just okay. So yeah, and well, we can just say that this is a positive constant, so it means that the sign of K naught doesn't change under this rescaling. Okay, and so if we just go back to cosmology, then we have to add the dependency on the cosmological time and write this in terms of well, these constants alpha and K naught, since this is a metric on a given well, this corresponds to the metric of the cosmological hypersurface sigma t, then it means that we have to restore the dependency on the cosmic time t, and well, this we have that as dx is something which is well, I can just put well, okay, I'm just going to rename, just to follow the traditional notation, this K naught bar, well, I'm just going to rename K naught bar and alpha to K naught and small a. I'm just going to this is just a renaming just to follow the traditional notation. So I'm just going to write here a square, and then this is k naught t r square plus r square. Okay, and therefore we deduce that the complete metric of the space-time is this one. Okay, so this is the metric which we have to input into the Einstein equations in order to obtain the dynamics of our cosmological model. Okay, this cosmological model was first used by Friedman in the 20s of the last century, and well, he published his model in a journal which in the end didn't have much diffusion, and so a bit later, also in the 20s, was the model was rediscovered by Lemaitre, and again it in the well, in the English-speaking world, this cosmological model wasn't studied, and it only gained diffusion worldwide when in the 1930s American mathematicians Robertson and Walker arrived to this cosmological model from a mathematical perspective. Well, they actually proved that if you assume homogeneity and isotropy in the universe, then this is the only possibility which you have. Okay, so in the end, given that the model was discovered by a number of people, cosmologies which arise from using this metric are called with this name. Sorry, it's just okay. So this just is formed with the initials of all the people who were involved in the discovery of this cosmology, right? Okay. Well, as we will see later, this is the basis of the standard cosmological model. But well, I would like to say something about the physics, about what an observer could experience, what a person who lives in this kind of universe could experience, or well, better said, how can we test whether we live in this kind of universe? Well, okay. To answer to this question, let me just say a bit more about the geometry of this model. Well, first thing is that this function is going to play an important role in the dynamics of the universe, and it's called the scale factor. Sometimes scale factor of the universe. But well, we will just use the name scale factor. And another thing is that, well, I wrote here this curvature parameter. Okay. I'm not sure. Just this. I will use the terminology curvature parameter for K naught. Okay. Well, the thing is that when we input this metric into the Einstein equations, we will deduce that this is actually a constant independent of the cosmological time. So from now on, you will see later the proof, but from now on, I will just treat this as a constant, and well, and I will call it the curvature parameter. Well, we explained this, that we explained before that this cannot tells us whether tells us what kind of hypersurfaces the cosmological hypersurfaces are. There can be flat hypersurfaces. They could be well, let me just explain this better. Okay, we saw previously that the geometry of the cosmic hypersurfaces is determined by the sign of K naught. So K naught positive, we saw that topology of sigma t is just a three-dimensional sphere. So in this case, we speak about an open universe. Okay. When K naught is 0, then sigma t is just a three-dimensional Euclidean space. I'm just going to use well, I'm not sure. Well, and so we speak about a flat universe. And if K naught is negative, then sigma t corresponds to the 3 hyperbolic space. And then we speak about sorry, this is closed. Sorry, I'm just sorry. This is closed universe because the sphere is compact, and what is the open universe is this one. Because open, because the hyperbolic space is non-compact. Okay, so K naught classifies the topology and geometry of the cosmological hypersurfaces into these 3 possibilities. Okay, right. Okay, we will see later which we will see later what which of these situations correspond to the standard cosmological model. But now, okay, let us just concentrate on the physics of these of these cosmologies. Okay. Okay. Well, we already know that our universe that a congruence, well, that the universe is threaded by a congruence of cosmological observers, which are geodesic congruence. Okay. Okay, and we also know that the universe is foliated by the cosmic hypersurfaces. Okay, right, and also the comoving we have a coordinate system on the comoving hypersurfaces. Well, in our model, in the comoving coordinates in this FLRW cosmology, the comoving coordinates which we are using are theta and phi. Okay, so these coordinates can be thought as coordinates on the cosmological hypersurface for each value of the cosmological time. Okay, right. Now the question is, suppose now that you have two points on the cosmological hypersurfaces P and Q. Well, just by looking at this picture, you realize that these 2 points will correspond to two different cosmological observers. Okay, and well, suppose that we want to compute the distance between the metric distance between P and Q. Okay, well, metric means this would correspond to the distance which you could measure with a scale or some other device. And well, how can we do that? Well, we can do that because we have the explicit form of the metric. Okay, so it's just we just need to use this form. Well, I'm just going to write this in a simplified way for our problem. I'm just going to write the metric in the form okay, where here, well, I'm just using the x notation for the comoving coordinates, and this hij is the metric tensor which corresponds to the just corresponds to, I think you can just guess what it corresponds to. Okay, but anyway, I'm just going to write it down. Okay, right, so that's what we have. And yeah, so how do we compute how do we compute this quantity? Well, the point is that these two observers have the same cosmological time. So this means is that we can just use the projection, well, the pullback. Speaking, if we just speak precursely, we can use the pullback of the full four-dimensional metric into the cosmological hypersurface. Okay, so and this is obtained by just setting dt to 0. So we obtain the pullback. Well, I'm just going to which is just this part of the metric. Okay, so yeah, so this is the metric which we are going to use to compute the distance between P and Q. And well, this is achieved. This is now a standard variational problem. Okay, we imagine that we have a curve which runs inside sigma t and joins P and Q. And well, of course we can compute the length of this curve, and then we will have to find the curve whose length is the minimum possible. Okay, okay? That's what we have. So if we call this curve gamma, okay, so we can we can parameterize gamma using the comoving coordinates. So just write the parameterization here. Okay, so this is, I'm just going to use okay, so this is gamma, and then for example we can just set just put for example, we can just think that gamma c at when s is equal to 0, this corresponds to the point P. When gamma is equal to 1, it corresponds to the point Q. Okay, right. So if we have this, then the length of gamma is just this is just standard differential geometry, which I suppose you're familiar with. So what we have is that this is have to evaluate the metric along gamma, and then the differentials will correspond to derivatives with respect to the parameter s. Okay. Well, the important point now is that here this this metric, this H metric, is not doesn't depend on the cosmic time t, as I mentioned before. So we can just rewrite this as follows. So you can just pull away the scale factor, okay, and write following. And now it turns out that this quantity here corresponds to the distance between P and Q along the cosmological hypersurface. So you can just write that. This is, I'm going just to denote this with this L. Okay. In the end, the conclusion is that the distance space-time distance is proportional to the distance taken on the cosmic hypersurface. Okay. Which actually this distance is independent on the cosmic time. It's just because the geometry on the cosmic hypersurface is independent from the cosmic time. Okay, so this is the final result. So we see here that the scale factor is telling us how the space-time distance between 2 points on a cosmic hypersurface varies. Okay, so what this means in physical terms is that if a person lives in one of these one of these cosmological models, what he will see is that objects which are around him are varying their distance with respect to him as the cosmic time changes. Okay, so that gives us a possibility to test whether our universe is really a FLRW cosmological model. Okay, but can we actually test that? Because as we explained at the beginning of the lecture, here by observers is meant objects of the size of galaxies. So is there a way of testing whether galaxies are, whether the distance between galaxies is changing with respect to the cosmological time? Well, the answer to that question is yes, there's a way, and this is what it is based on a consequence or a physical effect which takes place when in one of these cosmological models, and it's the so-called cosmological redshift. The cosmological redshift, which also it can also be a blueshift. I should right here. Okay, and what is this about? Well, as I'm saying, this is an physical effect which takes place in these cosmological models. And what is this? Okay. Suppose that we have two cosmological observers, P and Q, and these are the world lines of the observers. Okay. And suppose that at some cosmological time T sub E, the observer P emits radiation towards the observer Q. Okay, so we have that at cosmic time T sub E, P emits some radiation or light towards Q, which receives the radiation at a cosmic time t sub r. Okay, and suppose that some cosmic time later, which is t sub e plus capital T sub e, P emits again another pulse of radiation towards the observer Q, okay, which will be received at some time, which we shall call T sub r plus big T sub r, okay. Also, we will assume that T sub e corresponds to the period of the radiation. The emitted radiation as measured by P, by the observer P. Okay. Therefore, T sub r will correspond to the period of the radiation which the observer Q measures. Okay. Well, just remember that if we have a pulse of radiation, then the wavelength and the period are related by this formula. Okay, so this is the wavelength, this is the period, and this is the speed of light. Since we are working in geometrized units, well, we are going to take the speed of light as unity. So in this sense, this means that the period of the radiation coincides with the wavelength of the radiation. Okay, so when I speak here about period of radiation, I can also speak about the wavelength, right? Well, the aim now is to determine the relation between these two quantities, T sub e and T sub r. Okay, that's what we want to do. And how are we going to do that? Well, just erase this because we don't need this anymore. Okay. Well, first of all, we need to remember from what was just explained that the comoving distance between the observers P and Q is constant. It doesn't depend on the cosmic time. Okay. So I'm just going to this is one thing, and the other thing is that, well, I'm just going to write down the line element of the cosmological model in the short form, which we have already used in this lecture. Okay, so just remember that this is the metric on the comoving hypersurfaces, which we said that is independent on the cosmic time. Okay, so yeah, so this is what we need, and just and the thing is now that, well, if we evaluate this metric on a light ray, so we take that now that these coordinates are evaluated on a light ray, then it turns out that the proper distance is zero, as it's known from basic relativity. So now we can write that is now only on a light ray. And also, well, if we go particularize this to these light rays, which are going from two cosmological observers, then since this is the metric on the cosmic hypersurfaces, then it's possible to well, we can just use this to compute we can use this equation to compute this constant in the following form. I can just well, if we just project these rays, the word line of these rays is now we project it on a cosmic hypersurface, for example here in this one. Okay, so then we will have a curve. If we take this word line, this will give rise to a curve here in this I can, okay, I don't know what's the best way of okay, so we just project, and what it's it turns out that this length can be computed as well, if we just write this in this, if we just isolate this spatial, this metric, which is on the cosmic hypersurfaces, then we get this. Okay, and well, since now this is this since we, well, after doing this projection of the coordinates of the light ray, we get a metric now, which is the metric on the cosmic hypersurfaces, and now these coordinates are measured, are evaluated on the cosmic hypersurface, and are evaluated on a curve which is the projection of the light ray on the cosmic hypersurface. So we have to think therefore, if I now take the integral of this side of the equation between the emission time and the reception time, okay, then the integral on the other side will correspond to the distance, to the comoving distance between P and Q, okay? And well, this computation pertains to well, I wrote here on a light ray, but well, indeed, well, up to this point, it's valid for either this light ray or this other light ray. But if I do this, then this is only true for this light ray. Okay, this corresponds to this light ray. But I can do the same reasoning with the second pulse of radiation, and if I do that, what I get is this expression. I have now only need to change the times. And now, since the since the comoving distance is constant, then I can just write the same quantity on the right hand side. Okay. And this is for this is essential the property that these two quantities are constant, which we showed before. Okay, so from this we can just deduce that both integrals are the same. Yes, perhaps. So okay, so I can just write this property. Okay, that's what we have. And now, well, I have to remember a property of definite integrals. Well, if we have the integral of a function, and we have the integral of the same function, but with some different limits, and we subtract them, okay, then we can do a change in the integration limits. Okay, so this is a standard property of integrals, which you can easily prove. And so, well, I can just write this fashion. Okay, so, and now I can just apply this property to this expression, and it's just a matter of changing here the integration, the limit. So the integration, we have to change the integration limits. Okay. Right, so that's what we have. And finally, we can make an approximation, and well, as I said, this big TR and big TE correspond to the wavelength of the radiation, and the wavelength of the radiation is small compared with the variations in the scale factor. So what this means is that we can replace the integrals by their mean values. So we can just write this. And similar for the other integral. Okay, so if we just do these approximations in this expression, we get the formula sorry, this is dr. This is, here is the small gr. I have to take the and here is de. Okay, so and in this the final equation is dr de, or as I, since here big T's correspond to wavelengths, I can just write the same formula in terms of the radiation wavelength, which are measured by the observer and the receiver. Okay, so this is the result. Well, the thing is that with this experiment, with this experimental setup, we can relate, for example, if Q is us, then we can just relate the wavelength of radiation which we get from distant sources like galaxies with the scale factor of the universe. Okay, and in this fashion we can determine how the scale factor is changing. Well, for example, just to see that, it's perhaps convenient to write this into a slightly different form. Okay, so we have these relation, and then okay, for example, if the wavelength which we see which we measure is bigger than the wavelength of the radiation when it was emitted, then it turns out that scale factor increase since the cosmic time in which the radiation was emitted, and so we have that means that the distance between us and the emitting source increase. And this means that the universe has expanded. And of course, if we have an increase in the wavelength, this is called a redshift. Okay. Yeah. On the other hand, if the wavelength has decreased, then it's just the opposite. Scale factor has decreased since in relation to the scale factor of the universe when the radiation was emitted, and given that the distance between two points in the universe is proportional to the scale factor, then and so okay. So, and well, of course, this is the case which is called the blueshift, right? So, if we can relate wavelengths of radiation when it was emitted to the wavelength of radiation when it was received, we have information about the variation of the scale factor, and then we can tell whether the universe has expanded from the since the emission time or contracted since the emission time. Okay. Well, it's in practice. To study this, well, it's convenient to introduce a new parameter, which is the so-called theta. Z. Well, what is this parameter? Okay, this is just a definition, and well, from this discussion, we see that just put so we see that if theta is greater than 0, it means redshift, and if theta if z is greater than 0, it means redshift, and if z is less than 0, it means blueshift. Okay. Well, in practical terms, we know that we can compare wavelengths of between emitters and observers, because what is actually measured is the spectra of known elements. Okay, so the idea is that we measure spectra of known elements which are far from us, and what we get is a pattern which coincides with the spectra which we measure here in Earth, but which is in which the wavelengths are shifted, and that shift enables us to compare wavelengths of observers and emitters. Okay. Okay, so that's the way in which we can obtain this quantity, and then by just computing this quotient, we can we get the quotient between the scale factors, and we can decide we can know what has happened since the light emitted, we can know what happened, what has happened in the universe since the light emitted from the source occurred. Right. So well, actually, this was this experiment, these measurements were the first evidence that the universe is dynamic. That something was, and in fact, what the first time this was measured, it was measured in the 20s by Hubble. He discovered that in all the sources he studied, Z was positive, and therefore that means that we have a redshift. He always observed redshifts, never in distant sources. He always observed redshifts, never blue shifts. So what it means, according to our previous discussion, is that the universe is expanding. And therefore, this was the first experimental proof of the expansion of the universe. Okay. Okay, well, this is an experimental proof of the expansion of the universe, but it does that. Well, if we combine this with the observation that at large scale the universe is homogeneous and isotropic, then we have a good experimental support that the universe is described by the FLRW model. Okay. Well, in this context, it's useful to introduce the expansion rate of the universe, or Hubble parameter, which is defined as the derivative of the scale factor divided by the scale factor itself. Okay. Well, now, okay. Well, the thing is that what we need now is to obtain the dynamical equations of the universe, which are equations which enable us to obtain the actual variation of the scale factor with respect to the time, with respect to the cosmological time. That's what we are going to do next. This will come once we input the FLRW metric into the Einstein equations, and we will see that it's natural to write the equations in terms of the Hubble parameter. Okay. But well, to do that, we need to find the explicit form of the energy momentum tensor of the universe, which comes on the right hand side of the Einstein equations. Okay, right, so that's what we are going to do next. Let us discuss now the energy momentum tensor of the universe. Okay, if you remember, the Weyl principle stated that the only contribution to the energy momentum tensor of the universe is a fluid which is generated by the cosmological observers. Okay? Furthermore, we know that the cosmological principle tells us that the universe is homogeneous and isotropic. This the isotropy implies that the fluid has to be a perfect fluid. Well, I'm not going to review now the different kinds of fluids which one can work with in relativity and their properties, but I'm just going to remember that a perfect fluid is only characterized by its density and its pressure. Just remember, well, that's going to say that in, for example, in an isotropic fluid, pressure, we have different pressures which correspond to the different directions of space. Here, it's not the case because we are assuming that the universe is isotropic. Okay, so we can only have, that means that we only have a single pressure and also a single density. So that leads us to an energy momentum tensor which takes the following form. Where here u bar is the fluid velocity. Right? Okay, so that's what we need to take as the energy momentum tensor of the universe. But we have more information from the Weyl principle, which says that, from the Weyl postulate, which says that the fluid is generated by the cosmological observers. What does this mean? Well, it means that the fluid velocity coincides with the forward velocity of the cosmological observers. So it means that I can use the same symbol for the fluid velocity and for the velocity of the cosmological observers. Okay, right. So you can just delete the bars here. So we almost have the expression of the energy momentum tensor of the universe. Well, I say almost because we still need to determine the dependency of the density and the pressure. Okay, but this is easy because if we now look at the cosmic hypersurface, the cosmological principle says that that the density and the pressure have to be constant. Well, have to be constant. But with this I mean that they cannot change on when we move on sigma t. So the conclusion is that rho and p can only be functions of the cosmological time. Okay, right. And so well, this this is what this is all the information we can extract from the cosmological principle and the Weyl postulate. Okay, so so what we need to do now is to write the energy momentum tensor of the universe here in the Comoving coordinate in the Comoving coordinates which we are using. Well, we already have done that for the density and the pressure, and so in those coordinates we have to remember that the vector field, which is tangent to the cosmological observer's velocity, adopts a very simple form. Okay, so it's easy to realize that in the component notation, this vector field u is simply 1, 0, 0, 0. Okay. So then it's easy to obtain the expression of the energy momentum tensor of the universe in the Comoving coordinates with this information, and then input that into the Einstein equations. Well, before doing that and studying the dynamics of the universe, I would like to say a few words about units, because, well, I think at some point of the lecture I said that we are using geometric units, but, well, I'm just going to remember how these geometrized units relate to the standard units used in the international system. So, well, at the beginning of the lecture, I wrote the let me just okay. At the beginning of the lecture, I wrote Einstein equations. And the thing is that these are Einstein equations in geometrized units. Okay. Well, if in the international system, Einstein equations are almost the same. There's a little difference. Which is that we have here a factor which contains the Newton gravitational constant and the speed of light. Okay. Well, of course, in geometrized units, everything gets simpler because we don't have to write these constants in our formulas. But well, so that's the reason why I am using geometrized units in this lecture. But well, of course, when it comes to measurements and applications, units in the international system might be more convenient. So it's useful to have in our mind the relation between the two. So that's what I'm going to review now. So well, just remember that Newton constant has this value. I'm just adding this is the value of Newton constant in international system. Okay, and then we have the speed of light, which in the international system is taken to be this quantity. $299,700 299,792,458 meters per second, which is which in the international system is just a definition. Okay, well, the point that the thing now is that we can from this expression we can just read off the dimensions of these constants. Okay, so we have that. I'm just using the standard symbol, which is the square bracket to denote the dimension of a quantity, the physical dimensions of a quantity. So we see that gravitational constant has dimensions of length to the 3 divided by mass times square, and well, speed of light is just length over time. Okay, right. So well, the thing is that well, geometric units take G and C as unit. So what it means is that we are taking a different we're taking we're just taking length well, there are two things. Geometrized units take G and C to equal to 1, and then also they take length as the basic unit, so as a fundamental physical magnitude. Right? So if this is the case, what we need to do is, if we are taking length as our basic physical magnitude, what we need to do is use these relations and others to express the other physical magnitudes in terms of length and these quantities G and C which we have here. Okay, for example, in the case of time, this is evident. So we have that time is length over C. Okay, and then well, we can for example, we can now take this and this relation and replace it here and obtain the mass in terms of length. Okay, so I'm can just use so this is it, and then we just replace the time with this value, so we get that okay. So this is the relation between mass and length. Well, sorry, there was something which I forgot. Well, okay. Here I said that G and C is taken equal to 1. Well, the fact is what is not G is 8 pi G. Sorry about this. Okay, and was what is taken equal to 1 is this is because in the Einstein equations we have this factor. So what we need to, if we want to get simpler formulas, what we need to take equal to 1 is 8 pi G. Okay, So in the end, it means that well, I have to add this 8p factor here in this equation, and then I need to insert an 8pi factor here. So sorry about this, because I just forgot to count the 8pi factor in. So well, this is important because to relate formulas which are written in the geometrized units to formulas which are written in the international system, we need to take into account this 8pi factor. Okay, so yeah, so it's just have to just add the 8pi factor here. Okay, and so in the end, formula becomes this. Okay, so this is the relation between mass and length, and another thing which we need is the relation between energy and length. Well, for example, if we just remember the famous Einstein formula, which relates the energy to the mass, then in terms of dimensions, it means that the energy dimensions are related to the dimensions of mass by means of the speed of light, and so it's just now inserting this mass, well, inserting what we just obtained here. Okay, and so what we get is that energy is related to length by this expression. Okay, okay, so you see that it's possible to write if we take the length as our physical as our basic physical magnitude, we can write the other fundamental quantities of the international system in terms of length. And well, we just do that by using by using these two formulas to write the other physical quantities in terms of length. Okay, and so well, what I have done for time, for the mass, which is here, and also for the energy. And in this sense, we can also do that for energy density, because well, that's in the end, if we look at the Einstein equations, okay, we have the energy momentum tensor, and the energy momentum tensor, its units are those of energy density. Okay, so what it means is that well, when we work with the Einstein equations, we are working with the energy density. Okay, and well, Einstein equations tells us that the energy density is equal to geometry. Okay, because these all are geometric quantities. Okay, so we need to also have in mind the units of the energy density. Okay, well, of course, energy density is just energy divided by the volume, which is length to the power of 3. And so we just need to use this formula now to obtain that this is equal to well, just this factor, which is same, and then we get is 1 over length to the 2. Okay, so what this means is that, well, if we now work with well, all these equations which I have been written here are independent on any unit system convention. But now, for example, if we work with units in which we take gravitational constant and speed of, well, we take this 8 pi gravitational constant and speed of light equal to 1, then what we get from this expression is that the energy density has units of length to the minus 2, energy has units of length, mass has units of length, and time has also units of length. Okay, so and well, if we just look again at the Einstein equations, we realize that it's a very convenient choice, because, as I said before, Einstein equations are relating geometry with energy density. So the natural units for geometry are length, okay, because these quantities, all these quantities here, are just given naturally in terms of length. Well, okay, well, if you just remember that the energy momentum tensor has no dimensions. Okay, well, maybe I just can write this in this fashion. Okay, then yeah, the curvature is the derivative of the connection. Just going to write this in this way, which in turn is the derivative of the metric. Okay, so the curvature is the second derivative of the metric, derivative, of course, with respect to length, with respect to some coordinate system. Okay, so we conclude that the natural units of the curvature are length to the minus 2. Okay, so this means that in this equation, the natural units of the energy momentum tensor should be also length to the minus 2. And since energy momentum tensor represents energy density, we conclude that in geometrized units, energy density has natural units of length to the minus 2, which is what we are obtaining here. Okay, if we set all these parameters, all these constants, equal to 1. Okay, so that's why it's convenient to work with geometrized units. And well, the thing is that this formula gives us an easy way to go from international units to geometrized units, because well, as I was saying, these formulas are well, just are independent on any unit convention. So just write the formulas here. Okay, so we have this, we have this. Okay, so okay, so that's what we have obtained. And well, the thing is that if we have, for example, a quantity which has units of mass, and the quantity appears in some formula written in geometrized units, then we only need to use this formula to find the formula in international system units. It's just because we will know that the quantity will have units of length, and we only need to write length in terms of mass using this formula. Okay. Well, perhaps in this context, the simplest example is the case of the of the Einstein equations. Well, we said that when Einstein equations are written in geometrized units, the energy momentum tensor has units of length to the minus 2. Okay. Then, well, if you want to write now the energy, the Einstein equations in the international system units, then what we do is that well, we use this formula, and we just write well, we use this formula in which we isolate this factor. So we need to use okay, so that's what we have to use. And then it's just a matter of adding this factor to this expression, and then we get the standard factor, which is written in terms of the energy momentum tensor when Einstein equations are written in the international system units. Okay. And so the procedure is the same when we want to go from expressions which are written in geometrized units to expressions which are written in SI units. Well, we will, well, perhaps this is better understood when we will obtain the dynamical equations for the cosmological model, for the standard cosmological model. Okay, so that's all, and now we have all the elements to solve the Einstein equations, to study the dynamics of the universe through the Einstein equations. Okay. Okay, so we have to use now Einstein equations to find the dynamic evolution of the universe. Okay. Well, you know, this is a perfect fluid, so this is just what we uh, wrote before. Okay, and well, we have to input here in the equations the metric, which represents our cosmological model. And in this way, the variables which we need to solve for in the equations are the scale factor, the pressure of the fluid, its density, and the curvature parameter. Okay, so we are going to obtain equations for these variables through the Einstein equations. Okay, right. Well, I'm not going to do the detailed computations because otherwise the lecture would become too long. I'm just going to present the result. Well, it's just you can use your favorite computer algebra program to replace this metric into the Einstein equations, compute the curvature, and set the expressions equal to the energy momentum tensor. Okay. Just remember that you need to in these coordinates the fluid the vector field which is tangent to the fluid is given by this expression. Okay, so it's it means that the components are given by this relation, and so its covariant form is just I'm just going to write components, okay, or in coordinate free form is this form, okay, right. So this is now a matter of doing a computation. The first result of the computation is that the curvature parameter is actually independent on the cosmological time. Okay, you can just one of the equations will tell you that the derivative of the curvature parameter with respect to the cosmological time is 0. So the curvature parameter is constant along the cosmic evolution. Right? So if you use this information in the remaining equations, they will get simpler, and actually you can reduce the whole set of equations to only 2 equations, which I'm going to write now. Okay. right? Where I'm using just the standard notation of dot, meaning the derivative with respect to the cosmological time. Okay, right. So we have these two equations, and well, from now on, I'm just going to suppress the time dependency on the variables because it's clear from the context, right? And well, the thing is that we need to bear in mind an additional condition, which actually comes from the Einstein equations, which is that the covariant divergence of the energy momentum tensor is 0. Okay, so well, if we replace the expression of the energy momentum tensor, we just get this additional condition. Okay, it's equal to 0, right? Of course, since this condition is a consequence from the Einstein equations, and the Einstein equations are here, then, well, what I'm going to get by doing this computation could be also obtained by working with these equations, okay? But, well, it's sort of instructive to work out this computation and study its result, right? So, yeah, so this is just a computation which is very simple. Okay, so just well, to carry out this computation, we need to remember that since this vector, since this is the vector field which is in tangent to the congruence of cosmological observers, then we know from cosmological principle that this congruence is geodesic. So this is this vector field is a geodesic vector field, and in addition, it's parameterized with the affine parameter, because well, here, well, it turns out that well, in our coordinates, this operator corresponds to the derivative along the cosmological time, and the cosmological time is an affine parameter for this for the congruence of cosmological observers. Okay, so it means that this is a geodesic congruence which is parameterized with an affine parameter. So I can just put here 0. Okay, well, this is all standard relativity, but we need that information to do the computation, right? So well, this is just now a matter of expanding this and using this information here. Well, if you do the computation, what you get is this is just all very simple. Okay, so that's what you get, and well, we can now just multiply this equation both sides with u, and use again this relation. Okay, well, we use this relation, and well, since this is an affine parameterized congruence, then we also have that the norm of the vector field is -1. Okay, so I use this property here. Okay, and then and I use this property also, and so this becomes use the dot notation. Okay, so we see that b dot goes both is cancelled, and so in the end what we get is that okay, so this is the result, and well, we can now compute this quantity explicitly because we have okay, it's just a matter of replacing the vector u in its coordinate representation, and well, computing Christoffel symbols, and what you get is this relation. So this is in the end written in the form sorry, this is a plus sign. Okay, so this is the additional condition which you get, which we have to append to the other two dynamical equations. Well, I'm just going to do it here. Okay, so we have this. Okay, now I have to add this additional condition. Well, as I said, this is not really an independent condition because, well, it's derived from the Einstein equations. We did this through the computation of the covariant divergence of the energy momentum tensor, but you can also take, for example, if you derive this first equation and you eliminate the second derivative of the scale factor with this second equation, you are going to get again this third equation. Okay, so it's not really an independent equation, but well, I am adding it because it will enable us to write things conveniently. Okay, right. Well, now, well. These equations are the equations which describe the dynamics of the FLRW cosmological model. And well, yeah, that's all what we need now to understand the essential dynamics of the universe. So we no longer need to refer to Einstein equations anymore. So right. So what's next? Well, we are going to write the equations in a convenient form. Okay, which well, first let us well, the first equation is the so-called Friedman equation. Okay, so let us just take now Friedman equation here and compute its time derivative. Okay, so I'm just writing here Friedman equation, just suppressing the time dependency because it's already implicit, right? So this is and well, let us just take its derivative, its time derivative, Okay, and now we use this relation to replace the derivative of the density. Okay, so yeah, just for we have just okay. So I'm now taking this and just going to input here the derivative of the density. Okay, you have to make a bit more of room. Okay, so we have this expression. Well, you see that there is a cancellation here. Okay, so we have this. And then, well, you see that we can cancel the time derivative of the scale factor because it's in every term. Okay, and so in the end we are left with something okay, which is this expression. Okay, just okay. So we have an expression which relates the second derivative of the scale factor with something which contains no derivatives. Okay, so what we are going to do next is to well, we are going to we are going to use this as a dynamical equations. Okay, so in our list of dynamical equations, I'm just well, you see that we have an equation in which we have the first derivative of the scale factor, we have another equation which has a second derivative of the scale factor, and we have another equation which contains the derivative of the energy density. Well, I'm just going to replace this equation with the equation which we obtain, and so our set of dynamical equations takes the following form. We have the Friedman equation. Okay, just take away the time dependencies to make things simpler, because we already know that they are there. Okay, so we have but I just took away too much. Okay, we have this. Okay, so this is the Friedman equation. This is second dynamical equation, and then we have this additional equation, which, as I explained, it's not really independent from the other two, but it's convenient to have it in mind. You will see why later. Okay, right? And so, well, we have the dynamical equations of the universe written in a somewhat simpler form, right? Okay, this is the first step, and now, well, there's another issue about cosmological models which I didn't mention in the lecture, well, I have already explained the role of the scale factor, but what I did not say is that the scale factor has to be always positive. Well, this is clear from the expression of the metric. Well, just go back for a second to the expression of our cosmological model. Sorry. Well, it's not that it has to be positive. Well, what I mean is that the cosmological the scale factor has to be different from zero. It cannot be zero, because if it's zero, well, you see that this metric well, this metric becomes singular, okay? Because we no longer have a regular metric. But is it a true singularity in the sense that that the curvature tensor also becomes singular? Well, let us discuss this question briefly. Okay. This is sorry about this. This is, well, of course, if this is true, then it means that either we are in a situation in which the cosmological the scale factor is positive for all cosmic time, or the cosmological or the scale factor is negative for all cosmological time. We cannot have a situation in which the cosmological the scale factor becomes zero for some cosmological time, for the reason I just explained. And now the point is, well, we know that the metric is singular, but the fact that the metric is singular doesn't exclude the possibility of some coordinate change in which we can do an extension of our metric and get to a bigger region, of a bigger universe in which the case in which this is zero is included. Okay, so to answer to this, we need to study. We need to find out whether this set of the universe corresponds to a curvature singularity. Okay, that's what we have to find out. And well, a way of finding this out is computing the Kretschmann scalar for our metric. Okay, and well, you can do the computation. Again, this is a computation which I'm not going to detail. I'm just going to present the result. You can again use your favorite computer algebra program to do the computation, and this is the result. Okay. And well, now you can what we can do now in this expression is we can use this the cosmological equations, because well, this contains derivatives of the scale factor, and since we can just compute the first and second derivative of the scale factor by means of the cosmological equations, so just insert those derivatives here and do a bit of algebra, and what you get is, well, I'm just again presenting the final result. see that this is a positive quantity, and well, the thing is that if either rho or either if the density of the or the pressure diverge at some cosmological time, then the Kretschmann scalar also diverges, and we have a curvature singularity. Okay. So in any region well, if the cosmological equations imply that the density or the pressure diverge at some region of the universe, then we get a curvature singularity, and at that point it won't be possible to well, our model will lose its validity. Okay. Yeah. Well, in particular, well, this well, there are solutions of the cosmological equations in which this actually happens when the scale factor is 0. So in those models, as the scale factor equal to 0 corresponds to a curvature singularity, and it's not possible to extend the universe beyond that region. Okay. Okay. Let us leave aside for a second. Well, let us leave aside for the moment the question about the existence of a singularity, and let us now concentrate on the cosmological equations. Let us take Friedman equation, this equation, and well, let us use this equation to obtain the value of the curvature parameter. Okay, so this is just a simple manipulation. Well, it's just okay, and well, sorry, yes, there's some missing factor here. So this is right, and well, it shall be convenient to write this in terms of the Hubble parameter. Okay, so we can just use the to remember the definition of the Hubble parameter. Okay, so it's this So it means that this quotient is just the Hubble parameter square. Okay, right, and yeah, so we can get the value of the curvature parameter, and well, we have to remember that this is a constant. So this is this equation holds for any value of the cosmological time. So in particular, we can just take the cosmological time as our present time. Okay, so when we do that, we will just we will just represent quantities evaluated at present cosmological time with a zero. So this is just not, and the same for Hubble parameter. And well, we can just have density at the present time, pressure at the present time, and so on. Okay, right. So if we do that here, what we get is that it's possible to determine the curvature parameter if we know the present day values of the quantities which we have on the right hand side. Okay, and yeah, and not only that, we remember the significance of the curvature parameter. We remember that well, its sign determine the topology of the universe. Okay, just remember that this is the closed model, closed universe. And okay, so well, this was discussed previously in the lecture, right? So it means that if we know percentage values of these parameters, we know something about the topology of the universe. Okay, so yeah, so it's just well, just notice that the sign of this is always positive, so it means that we can just get rid of it when we study the sign of the curvature parameter and write this in the following form. Okay, okay, so the knowledge of these well, the matter energy density, Hubble parameter, and cosmological constant in their present day values means that we know whether the universe, the topology of the universe is closed, the topology of the universe is flat, or the topology of the universe is open. Well, of course, I'm speaking about global topology. Right. Okay. So well. Yeah. So well, we can just write this in a slightly different form. Well, these conditions. So well. So what this tells us is that in the end, everything boils down to know the present day matter energy density and compare it with the value of this quantity, which is here on the right hand side of these inequalities. Well, this quantity is the so-called critical density. Okay. Okay, so what this tells us is that if the present day matter energy density of the universe is greater than the critical density, then the university is the universe is closed. If it's equal to the critical density, the universe is flat, and if it's less than the critical density, the universe is open. Okay. Well, okay, just a comment. I'm well, in many textbooks, they take the cosmological constant as contribution to the matter energy density of the universe, and they include it in the definition of the critical density. So what you will see a definition of the critical density, which is just this, okay, but it's just because they are considering this critical density. Well, they're including the cosmological constant as part of the critical density in this definition. Okay, but I am not doing that. I am in my lecture. I'm always keeping the cosmological constant as something separate from the matter energy contribution. Okay, so that's the reason. If you that's the reason why this definition differs from the definition which you will see in some textbooks. Okay, right. Okay, so the first this is the first what is the first important point which we get from the cosmological equations. I can or determine the topology of the universe, and well, and also, well, it will be convenient to replace the value of the curvature parameter, which is contained in the Friedman equation, by this expression. Okay, so let's go back to the Friedman equation, which is here. Okay, and to the replacement, well, since this is written in terms of the present day Hubble constant, we are going to also write the Friedman equation in terms of the Hubble Hubble parameter. Well, just this is also simple. We have just to divide everything by a square, and we get that okay, so we're just going to write this as okay, right, where I just use this definition, and now this, well, of course, this is the Hubble parameter at any cosmological time. Okay, so now I'm just going to take this equation and do this replacement. Okay, so let me just write down the equation here. Okay, well, it's convenient to before doing the replacement, it's convenient to isolate the Hubble parameter. So what I have is this okay, and now I'm just take curvature parameter, which I obtained previously, and replace it here. Okay, so I have to take this expression and input it here. Okay, and if I do that, I get the following. Okay, so continues here. Okay. No, okay. So this is what we get. We get the Friedman equation written in terms of the Hubble parameter. The Hubble parameter at any cosmological time, and well, we can just think of this as a relation which gives us the Hubble parameter at any cosmological time in terms of the Hubble parameter at the present cosmological time, or at the cosmological time which we regard as the present cosmological time, plus the matter energy density at the present cosmological time. Okay. Okay. Right. Well, it's also possible to write this quotient in terms of the redshift parameter. Well, if you just remember that when we studied the redshift, the definition of the redshift, just remember this relation. Okay. Well. Well, okay. The actual relation is just to well, the actual relation is just to follow the notation which I use when I introduce the redshift. Okay, where this T sub r is the reception time, and T sub e is the emission time. Okay, right. Well, the thing is that in this context, we can take the reception time as the present cosmological time. Okay. And the emission time any other cosmological time. In this sense, this equation just becomes this. And well, you from here, you realize that it's possible to replace this quotient with the redshift, and also what it means is that we can express this equation in terms of the cosmological redshift. Okay, but I'm not going to do that. I'm just telling you this because sometimes you'll see this equation written in terms of the redshift. Okay, so that's why I'm mentioning this now. But I'm not going in this lecture. I'm not going to do that. Okay, right. So this is what we have, and now to proceed now, I will we need to make further hypothesis about the matter content, about the behavior of the matter content of the universe. Okay, we need to introduce further assumptions. Well, and what are those assumptions? Well, well, just if we look around us, mm, the kind of matter which we see is non-relativistic matter. Well, what does it mean? Well, what this means is that the matter has no interaction with the radiation. Okay. Well, essentially, well, if we look at around us, we see matter and radiation. Okay, that's what we see in the present day universe. Well, yes. Yes, we see the matter, which is stars, planets, so on. And then radiation comes mostly in well, form of can be visible light, but well, okay, all kinds of radiation. Okay, and the thing is that these two contributions don't interact with each other. Okay, they are kept. We don't see globally that matter and radiation are transforming on each other. And when that happens, we speak about we say that the matter is non-relativistic matter. Well, well, the word non-relativistic, what really means is that the energy of the matter is not enough to start the interaction, matter radiation. Okay. Well, of course, this is well, as always, we have to remember the cosmological principle, and this holds at large scale. Okay, if we look at the universe at a smaller scales, for example, in the interior of a star or the center of the galaxy, this hypothesis is not true. Okay, and but if, when looked at larger scale, and when the universe is looked at larger scale, we see that the matter is non-relativistic, right? Okay, so that's what that's the hypothesis that we are going to make. And okay, how does this hypothesis carries to the cosmological equations? Well, to answer to that, we need to find out what the matter contribution to the cosmological equations is, what the radiation, what the contribution of the radiation to the cosmological equations is, and then add them together. That's what we have to do. Okay, so well, and what is the contribution of the non-relativistic matter? Well, well, the way in which non-relativistic matter is modeled is as matter which has no pressure. Okay, so it means that for that matter, the energy momentum tensor, well, I am going to write this, well, I can, right, so I'm just going to use the notation. This is the notation of the energy momentum for the energy momentum tensor of non-relativistic matter. And well, for this matter, we have that the energy momentum tensor takes this form. So it's just that it's, well, I'm just going to put this downstairs. Okay. So it means that the pressure is zero identically. Okay. Well, suppose for a moment that the universe was composed only by non-relativistic matter. Okay, so let us forget about radiation contribution, and so let's assume for a second that this is the only contribution to the energy momentum tensor of the universe. Well, what that means is that we will have to to study the dynamics of such a universe, we would have to just set the pressure to zero, okay, in the cosmological equations. Well, and then, well, you just, if you remember, one of the cosmological equations is this one. Okay, just remember this cosmological equation. So if we set the pressure to zero, then what we get is this equation. Well, and the thing is that this is an equation which is very easy to integrate. Okay, so yeah, you just it's immediate to solve this differential equation, and the result is given by this expression, where this capital A is an integration constant, which well, we can write in terms of the present day matter energy density. So if I just do if we evaluate this equation at present cosmological time, what we get is that okay, well, in this case, the zero will, since I have already put the m downstairs, I am forced to put the zero upstairs. Well, I was before I said that I was going to put zero downstairs to indicate present day quantities. Well, to indicate quantities evaluated at the present cosmological time, but here I'm afraid I will put the zero upstairs. But okay, I think that there's not going to be any confusion. Okay, so then we have that this is this, and then we can just write the integration constant in this form, which leads us to this value. Okay. Okay. So if we know the in this cosmological model, if we know the matter density at present cosmological time, we know the matter density at any other cosmological time in terms of the scale factor. Well, actually, if you, well, it's even possible to solve the to obtain the explicit expression of the scale factor in terms of the cosmological time if you use this information in the remaining cosmological equations I'm not going to do this in this lecture because otherwise the lecture would last many hours. But I'm just going to, I'd like just to mention that that is possible. And well, actually, this is found in many textbooks. What I would like to stress here is that when the scale factor is 0, this diverges. Okay, so from this expression, you easily see that okay, and so if you remember what I discussed previously regarding the existence of a singularity when the scale factor is 0, then well, you conclude that since the matter energy diverges when the scale factor is 0, then from our previous result, we see that Kirchmann scalar diverges when scale factor goes to 0 in this cosmological model, and so in this case, A equal to 0 corresponds to a physical singularity. Well, to a curvature singularity, which is normally regarded as a physical singularity. So in this model, there's no hope of going beyond the region in which the scale factor is 0. Okay. Okay. So this is a very summarized description of a cosmological model in which the matter has no pressure, which is so-called non-relativistic matter. Okay. Right. So and now, well, let's now assume that we have a universe which only contains radiation. Okay. So let us now turn to the study of a radiation universe. Okay, in this case, what is the form of the energy momentum tensor? Well, for radiation, well, it's this is also known that in this case the density is related to the pressure by means of this relation. Okay. Right. Well, okay. I'm not going to spend time discussing why this is so. Well, okay. It's not really well. If we assume a perfect fluid, because well, we are assuming all the time a perfect fluid. Well, radiation is generated by the electromagnetic field. Okay. So it means that well, if you remember. The expression of the energy momentum tensor, which is created by the electromagnetic field, well, it turns out that for this expression, the trace of the energy momentum tensor has to be 0. Okay, just take the trace of. I'm just going to write this fashion. Just take the. Okay. And since if you impose this condition on the expression of the energy momentum tensor which you have for a perfect fluid, then you are going to obtain very easily that this relation between the energy density and the pressure has to be satisfied when this is true. So this is the relation which we need to impose when we work when we are in a universe which is composed only of radiation. Okay. So so now what we do is just repeat the computation which we did for the non-relativistic matter. Okay, so it's just we take again this equation and yeah, and impose this condition here. Okay, well again, this is a very simple computation. Okay, just put okay, so and well, again we obtain an equation, a differential equation, which can be integrated very easily. Okay. Again, capital A is just an integration constant, which we write in terms of present day conditions. Okay. Well, sorry, just forgot to. So this results in okay. So this is what we get for for the matter energy in a radiation universe. Well, again, you see here that well, it's also possible to if you substitute this into the other equations, into the other cosmological equations, you can actually solve for the scale factor. You can obtain the time evolution of the scale factor, but I'm not going to do that in this lecture because we don't have enough time. I'm just going to mention that again when the scale parameter goes to 0, then the matter energy density diverges, and so again, for the same reasoning as before, the set in which the scale parameter is 0 corresponds to a physical singularity. Okay. Right. Another thing which I would like to mention is that, well, in the same way as we can do with the Friedman equation, this quotient here can be written in terms of the cosmological redshift. Okay, I'm not going to do that. The same happens for the matter for the non-relativistic matter universe. This quotient can be written in terms of the redshift. I'm not going to do that in this lecture, but you can you might find this kind of expressions if you look into textbooks. Okay, so the conclusion of this is that we know it's possible to determine the dynamics of the universe when it only contains non-relativistic matter, and it's also possible to determine the dynamics of the universe when it only contains radiation. It's just simple integration. But now let us make use of our hypothesis, okay, which says that the universe is composed by non-relativistic matter. It's composed by non-relativistic matter plus radiation. Okay. Well. Okay. Well, I'm just going to take this. Put it here. Okay. And then right. So this is the hypothesis. Well, don't need to put this. Okay, so the universe is composed by non-relativistic matter and radiation, and then right, we have already discussed the particular case in which the universe is composed by only non-relativistic matter, and the universe is composed by only non-relativistic radiation. And so how do we work with this case in which we have both? Well, since the matter is non-relativistic, then what we assume is that the total energy density of the universe, okay, now it's this is just the energy density, the total energy density of the universe is just the sum of the contribution which comes from the matter and the contribution which comes from the radiation. Okay. So we only need to replace these values, these contributions, by the values we found above. Okay. So the matter is just okay, so okay, right. So this is what we get, and now well, and now it's just what we have to do now is to use this into the cosmological equations. Well, we also well, in the case of radiation, we also have the pressure. Well, just have well, okay. I didn't mention this when I discussed the radiation universe, but well, of course, if you know the density, the matter density, then you just use this relation to get an expression for the pressure. Okay, so it's just okay, so you have this expression for the pressure by just using the relation between the matter and pressure in this universe. So and in the complete universe, the matter doesn't have any pressure, and the radiation has this pressure. So we deduce that the pressure is just this value here. Okay, so can just add it. So the conclusion is that under this hypothesis, we have these expressions for the energy, for the matter density and the pressure, and so we can just replace these expressions into the cosmological equations and use them to establish the dynamic of the universe. Okay, right. So well, if we go to the Friedman equation, well, we have well, let us just collect the expression which we had for the Friedman equation, okay, which is this one, right? So so it's just a matter now of using this information into the Friedman equation, okay? So well, of course, from this we deduce that the percentage density is just the sum of the matter percentage density plus the radiation plus percentage density, okay? So yeah, so that's what we have. Okay, and then okay, so just going to replace just going to replace the density with this expression. Okay, so this is then I have this, okay. Right, so just complete this. Okay, and now, well, let us just write this equation in the following form. Then okay. Sorry, I just forgot to add m here. Okay, sorry, there's no so a typo here, okay, and also here, okay. Okay, so this is Friedman equation, and well, it's convenient now to define to make the following definitions. We introduce to simplify this equation. We introduce the following dimensional quantities. Yeah. Well, um, well, it's clear that in terms of these dimensional quantities, this equation uh, gets simpler, but also it's clear that mm, if we add all these dimensional quantities, we get unity. Okay. Well, just remember that we have this, and well, uh, the reason why we introduce these quantities is not just to simplify this equation, but also that they play an important role in the dynamics of this cosmological model, because well, just by looking at these relations, we realize that they are directly related to the matter radiation contributions to the universe in our present epoch, and well, and they are also related to the cosmological constant and to the geometry of the universe. Well, just have to remember that uh, these just have to remember the expression of the uh, curvature parameter of the universe. Well, I have it somewhere. Yeah, so it's this expression here. Okay, so if we just go back, and put here this expression. Okay, we just realized that this omega is well, okay, maybe it's easier just to write. Okay, just going to okay, so you see that we have here the same factor, so we can just we have that omega this quantity is just okay, no, this is this. Yeah, okay, so that's why we are calling this omega. Well, I should have perhaps chosen the notation k naught, but well, I'm just going to follow the traditional notation and use omega k here. But this k, well, is just because in many textbooks what I'm calling k naught is just called k. Okay, so that's why it appears here k. But anyway, the important point is that this quantity is directly related to the curvature parameter of the universe, and then is related to the topology of the universe. Okay, right. So well, as I'm saying, these quantities, these dimensionless quantities, will play a role in the dynamics of the universe. I have already said something about it, but we will see it in full detail when we study the this equation. Okay, when we study this equation written in terms of these quantities. Well, yeah, okay, so it's just doing the replacement, and I don't need this anymore, so I delete it, and then just write the final result. Okay, so this is just a Friedman equation written in terms of these dimensionless quantities. Okay. Yeah. Okay. Okay. So this is what we get, and in fact, well, before discussing this, well, we can just simplify it even further if we do a change of variable. Okay, so if we do the following change, okay, okay, we rescale the scale factor and write it in terms of rescale factor, which I will call capital A. Don't confuse with the integration constant which I used before. Okay, so I'm just going to and we can also rescale the cosmological time and define a new cosmological time, which is rescaled by the Hubble parameter. Well, okay, maybe it is clearer if I just put it. Okay, and so if you do these replacements into this equation, you can get a simpler form of it, which I'm just going to write down now. Okay. Well, now this is not in this. The question is not in terms of the Hubble parameter, but it's in terms of the cosmological rescale time. Well, okay, I have this. Okay. Well, I'm just going to put some terms on the left hand side of the equation, and I'm just going to leave omega k on the right hand side of the equation. Okay, right. Well, okay. Right, and so, well, in this fashion we have obtained an expression of the Friedman equation which is it's very simple, and in which the behavior of the solution it's determined by the values of these dimensionless parameters omega, which I introduced before. Well, just recall that these dimensionless parameters are all constants, which are obtained in terms of quantities which we measure in the present day universe. Okay. So in this context, we can regard them as constants. Okay. Well, before discussing the implications of this important equation, let me just show the result of writing the other cosmological equations in terms of these new variables. Okay. Well, just remember that we just go back to the cosmological equations, just to recap what we have been doing. Okay, yeah, these are the cosmological equations. This is Friedman equation, which we have already written in terms of the new variables. The information coming from this equation has been already used when we imposed the hypothesis of matter being non-relativistic and not interacting with the radiation, because we use this equation to integrate. So what we need to do now is to use this equation and write it in terms of the new variables. Okay, so okay, so I'm just going to put this equation here, right? And yeah, so again, this is the second cosmological equation, and well, it's just now we have to first replace the matter energy density and pressure by these values, and then write what we get in terms of the omega constants. Okay, so I'm just going to put it this. Okay. Right. So I have to make a bit more of room. Well, we no longer need this, so I can just delete this part. Then, yeah. So this is okay. Sometimes it's a bit. So we have this and this, and then okay. So it's just input this we have to just input these relations here. Okay, just do some intermediate computations, but well, it's just very simple. Okay, so okay, so this is what we have. And okay, so now just use the definition of omega, of these omega quantities which we introduced above, and write this in terms of the omega quantities. Well, if you do that, what you get is the following. And we can now do the rescaling, which we did in previous equation. And well, if you well, okay, what is just to remind, well, just introduce the rescale scale factor and the rescale cosmological time. And well, if you do that, the final result is this one. Okay. Okay, so in the end, the cosmological equations are reduced to these two. This one. Yeah, this one. Okay. Which are given in terms of the omega parameters. Okay, well, this as we know, these equations were obtained under the hypothesis that we have that present-day universe has non-relativistic matter, and that the matter does not interact with the radiation. Well, this kind of non-relativistic matter is also called cold dark matter. Well, okay. I will explain the meaning of this in a moment. Okay, the name, well, cold is because when matter and radiation don't interact, it's because well, if matter and radiation don't interact, it's because matter is cold. Okay, so and the term dark, well, we will understand. Well, this has to do with the measured value of this parameter omega m. Okay, so it means that okay, well, we will explain this later, but it's just for the moment. Just say that this omega m doesn't come only from the matter which we can see. There is a contribution to it from matter which we cannot see, and this matter which we cannot see is called dark matter. Okay, so that's why this dark is here, and okay, and also well, this is just another name for the hypothesis about the matter which we did to obtain these equations. Okay, so it's just to say that well, it's just to mention that there is another terminology for that hypothesis. And the cosmological model which arises from this equation is the so-called ΛCDM model. Okay, well, CDM is just an abbreviation for cold dark matter, and lambda is because we are assuming that the cosmological constant lambda is different from zero, and so what it means is that this omega lambda, which is just the cosmological constant contribution, is different from zero. Okay. Right. Uh, Now, okay, so these are the equations for the lambda CDM model, and now the issue is now, well, try to determine what the values of these parameters are, and how this model really fits with the experience. Okay, so now so let us do that next. There is an important issue which I forgot to mention regarding these equations, and it's that this equation is just the derivative of this other equation. Okay, just this is just a simple computation. So to study the dynamics of the universe, we only need to look at this equation, which just remember that it comes from the Friedman equation. Okay, and so. But the reason why I am keeping this other equation is because it also gives valuable information regarding the curvature of the scale parameter. Okay, well, we'll understand this a bit later. But now, so now let us just concentrate on this equation, and well, we can extract qualitative properties of the solutions of this equation if we realize that it has the form of conservation law. Well, it has the form of a conservation because, well, this is a constant, and if we just take this as a potential, okay, so if we define this, including this minus sign as a potential, then the equation just takes the form of a conservation law. Okay, so if we regard this as a kinetic term and this as a potential term, then we have a conservation law, and this enables us to study the qualitative behavior of the solutions if we know the form of this potential. Okay, and the form of this potential is completely determined once we know the values of the omega parameters, which, as I said before, they can be measured experimentally. Okay, right. This is the main. This is the way in which we study the solutions of this equation. And well, before concentrating on the specific form which has been measured for this potential in our universe, well, we can already say something which is valid for any value of these parameters, and it's that if A, the capital A is approaching 0, then well, it turns out that the potential behaves like this. And so what this means is that the only significant contribution to dynamics is coming from this term, which, if you remember, this omega r is defined from the radiation contribution. So what this means is that when A is close to 0, then the dynamics of the universe is determined by the radiation part. Okay, and also when capital A goes to infinite, then from the potential can be approximated by this term, which well, it's the term coming from the cosmological constant. Okay, so what this means is that the dynamics of the universe will be dominated by the cosmological constant contribution. Okay, right. So we just well, of course, this asymptotic behavior assume that both omega r and omega lambda are different from zero. Okay. Therefore, well, as we are going to see next, this is what actually happens in our universe. But okay, so we can already, regardless the value of regardless the actual values of the parameters, we can already draw a first picture of the potential. Okay. Okay, so if A goes to 0, then we will have something like this, and if A goes to infinite, then we'll have something like this. Well, of course, this is assuming that well, this is indeed the case. If you look at the definition of omega r, you immediately see that this is a positive quantity, and for this to be true, we need that cosmological constant is positive. And well, we will see that this is also indeed well, experimental data support that this is indeed the case. Okay, so we can establish the asymptotic behavior of the potential with these conditions without knowing the actual values of the parameters involved, right? Okay, so yeah, so now the dynamics. Well, if we have this generic picture of the potential, then the dynamics will be determined by the value of these omega k, of these, which well, once again, I remember that it's related to the curvature parameter of the universe, which we have. Well, okay, here's the actual relation. Okay, so just going to put it here. Okay, so okay, so according to the, depending on the value of this constant, then we will have, for example, we will have different possibilities. For example, if we suppose that this is omega k, Okay. Then the dynamics can only happen for values of big R lying in this region. Okay. So this will be the only so these values of capital A will be the only values allowed by the dynamics. This is just a standard analysis of which, which you have in classical mechanics when you have a particle which moves in a potential. Okay, well this is exactly well this equation is exactly the same one, and so just by looking at the representation of the potential and the value of this quantity, which would represent the energy, total energy of the particle, then we can see the regions in which the particle could move. Here the particle is just this scale factor, and so we can see the regions in which the scale factor can vary. Yeah, in this particular case, we have already seen the regions. Well, in this, well, if we look at this region, I just mentioned when the scale factor goes to 0, then the dominant part of the potential is the one which comes from the radiation. Well, when we studied the case of the radiation, well, just remember that we deduced that in that case, when the scale for the case of matter which is composed of radiation, when the scale factor goes to 0, then the matter density diverges. This was studied before in the lecture. So what this means is that in this diagram, in this picture, when the case A equal to 0 corresponds to universe radiation dominate universe. Well, case approaching 0 is just and then we established previously in the lecture that the matter density of the radiation diverges when the scale factor goes to 0. So the conclusion is that in this case the value big A equals 0 is a curvature singularity, and therefore the dynamics cannot go beyond A equal to 0. So it means that dynamics is only confined to a compact to this compact interval. Let us just to make things clearer, let's just call this a bar, for example, and then if this is a bar, the dynamics can only take place in this compact interval. Okay, and therefore, okay, in the well, in this okay, well, if we, in this interval, if we look at this side, but of course, if this is just well, okay, let me just call this a bar 1, then of course in this case mm, well, the dynamics takes place if we look at this part of the picture, we see that dynamics also takes place in this other interval. Okay, so the interpretation of this is that in this case, in this part, it means that scale factor starts at 0, and then it reaches a maximum value in which a bar, in which scale factor equals a bar. Okay, and then it it decreases back to the value 0. Okay, well, if you just well, or in other words, the universe cannot expand to a scale factor to a value of the scale factor which is bigger than this a bar, this value given by a bar. And here, in this other part of the dynamics, we see that the universe could well, if there is a period of contraction in the universe, then this contraction cannot happen, cannot go all the way down to the scale factor being 0. The scale factor will attain a minimum value of which is given by this a bar 1. Okay, well, this is exactly the same same discussion which one has when one discusses the motion of a particle in a potential. Okay, and well, of course, we have the situation in which this constant is actually never intersects the potential. Okay, and then if we have this situation, then of course the dynamics is no longer well. The dynamics can now take place in the whole positive interval for the scale factor. Just put this. And then yeah, well, and then well, we don't have the situation in which the universe expands to a bigger value of the to a maximum value of the scale factor, and then contracts back, or there's a minimum value of the scale factor. Scale factor can take any value. Okay, and so in this case, it's not possible recontraction of the universe or a minimum expansion of the universe. Okay. But in any case, well, since we have this property that that when scale factor goes to 0, universe is radiation dominated, then we will still have the singularity, which we know exists. So it's not possible to extend the scale factor to negative values. We have to work always with a positive value of the scale factor. Okay. Or well, of course, here if we do well, of course, I could have we could have chosen another convention and worked always with negative values of the scale factor. but in this case, well, this just amounts to choosing a different convention. Okay, but well, in any case, it's not possible to let the scale factor vary in the complete real line. Okay, so well, this is just a rough description of the dynamics of the universe. Well, mm, mm, well, let me just present the potential for the measured values of these of the parameters. Okay. Well, the most well, I took the what I think are the most recent measurements, which come from the uh, uh, Wilkinson microwave anisotropy proof. Well, I'm not going to enter into any details as to how the measurements are done. I'm just going to present the results of the parameters and use them to discuss the dynamics of the universe. Okay. Well, just giving the values. Well, okay. Maybe I think it's better to just. Okay, so this is the curvature parameter. The matter contribution is split in two parts, which is the matter, the so-called baryonic matter contribution and cold dark matter contribution. Just going to write first the baryonic matter contribution. And then the cold dark matter contribution. Okay, and the addition of these two is what I have called in this lecture the matter contribution. Just keep the same significant digits as in these measurements. Okay, and then, well, the radiation contribution is, well, is just obtained from the other parameters. Need something like okay. So these are the measured values of the contribution of the different parameters. Well, why is this distinction made? Well, the thing is that baryonic matter is matter made by baryons. Baryons are 3 quarks, and well, the matter which we know is all composed of baryons. So this matter is what we might call the familiar matter, well, planets, stars, galaxies, us. The thing is that it's the matter which we can which we have measured here on Earth and which we see with our telescopes. Well, the thing is that this matter is insufficient to account for the dynamics of the universe. We need to, well, we need something else to account for the dynamics of the universe. And this something else is given by this contribution, which is the so-called dark matter. Well, nobody knows for sure what dark matter is made of. Okay, so what we know is that we needed to explain the data, and so that's the reason why it is called dark matter. Dark because we don't know what it is. And well, if we just well, the total matter the total matter contribution of the universe is mostly comes mostly from the dark matter. Okay, and also we also but we also see that the total contribution or the total matter energy of the universe is mostly comes from the cosmological constant, which is roughly 70% of the total. Well, I don't remember if I have said this in the lecture, but the thing is that cosmological constant contribution to the Einstein equations is sometimes put inside the energy momentum tensor, and so this is sometimes regarded as matter as a kind of special matter. Okay, so or a kind of special energy. So this sometimes is this contribution is sometimes is called dark energy. Well, dark because, well, this is just a kind of energy, but we don't know exactly what it is. Well, we know it's related to the presence of a cosmological constant in the Einstein equations, but its true nature is still a mystery in physics. Okay, we know it's present in our equations, but because we needed to explain the dynamics of the universe, but its true nature is still unexplained. Okay, And we see that it accounts for the most important contribution to the total. It's just 70%, much higher than the matter contribution. And in the matter itself, we still have this mystery of the dark matter. So we have dark matter, dark energy, which we don't know what it is, and it turns out that these unknown substances or things are the principal responsibles for the dynamics of the universe. Okay, and that's finally, if we look at the contribution of the of omega k at the contribution coming from the curvature, just notice the errors, that the errors are actually higher than the actual measured value. So indeed, we can say that approximately this parameter can be taken to zero, or what better said, that zero is consistent with the measure value for the curvature parameter. Okay, right. So this is these are the values, and so we can now represent the potential with taking these values. I'm just going to show a graphical representation of the potential for these values. Okay, so yeah, here it is. Okay, so you only have to insert the values on the formula which gives the potential, and yeah, so this is the zero, the origin of both A and the potential, and so given that we are taking the curvature parameter equal to zero, then we could, to discuss the dynamics of the universe, we could just have we can just take the energy of the particle, which would correspond to the dynamics, coinciding with the horizontal axis. Okay, so that's what we have here. Right. Okay. So right. So just connecting with the discussion which we did before about the dynamics, we see that now we have a dynamics in which the scale factor varies in the in this infinite interval. Okay, and yeah, and so there are dynamics starts when A is equal to zero here, which is the which as we discussed, it corresponds to a singularity, and then we don't have a maximum expansion of the universe or a minimum expansion and then a recollapse. So this means that the universe will expand. In these dynamics, we will have an indefinite expansion of the universe. Okay. Well, there is something which I didn't say about the asymptotics when I discussed the asymptotic behavior of this potential. Well, if we look at I already mentioned that when scale factor is close to zero, then we have the universe is radiation dominated. And well, for large values of the scale factor, the universe is dominated by the lambda contribution, which, as I just discussed, it corresponds to the dark energy. Okay, and so we have this region in between. Well, if we look at the expression of the, well, just remember that we had another expression for the second derivative of the scale factor, and well, if we look at that expression and we evaluate it in this regime when a is large, then just simple computation shows that we have that this just coincides with omega lambda, which well, this is positive, so it means that the second derivative of scale factor is positive, and therefore we have an accelerated expansion. Okay, so just because, well, we just represent the scale factor against time. Okay, against this rescale time. Well, it's going to look something like this, and it's when a is big. Okay, because this just corresponds to the positive second derivative, and well, of course, this would be still true for if we just take our original variables without any rescaling, and well, this well, this can give us an estimate of well, if we take the present well, if in the present time we are in this regime, okay, then we can just well, this is then a naught. Okay, have to make this bigger. Well, then yeah, we can use well, if the present time lies in this regime, then we can just give an estimate of the value of the cosmological of this of T naught if we just compute the tangent to this curve. Okay, because well, okay, this tangent, well, with this will it corresponds to well, if we just take, well, the tangent is just the derivative at T naught, and it corresponds to well, just look at the picture, A naught divided by this distance, which I will call x, okay, and then, well, we see that x is just A naught divided by, which is the inverse of the present day of Hubble parameter. Okay. Well, well, and this x, of course, is smaller than T naught. So if we compute the inverse of the Hubble parameter at T naught, then we know that it will be bigger, would be smaller than T naught, which is the which corresponds to the age of the universe. Well, because the thing is that well, in this setting, okay, well, I already said that a equals 0 is a singularity. This is so-called cosmological singularity, okay. And since the dynamics implies that A is within this interval, we see that the solution of which comes from the equations will become 0 at some value of cosmological time, free scale cosmological time, which we are free to take as t equals 0. Okay. Then so this t equals 0 is the so-called initial time. Well, I'm just going to use the unscaled cosmological time. And so, well, so t equal. You can also say that this was the time in which the universe was created. Well, but anyway, and so in this case, the value of, if we take t naught as the present cosmological time, then since t equals 0 was the corresponds to the singularity, then we can call this t naught the age of the universe. And so it turns out that the age of the universe, if T naught is in this region, when it's dominated by the dark energy, then the inverse of the Hubble parameter will give us an estimate. Will give us a lower bound for the age of the universe. Okay, right. So. Yeah, and so, well, we can test this experimentally, because for that, well, we just need to measure the expansion of the universe and test whether this is true. Okay, this is, well, of course, well, if this is true, then the scale factor looks like this, and we can apply this. Well, the opposite case occurs when we are on this side of the potential, because on this side of the potential we well, we have the radiation dominant regime, and well, you can see that in that case, well, I'm just going to write it here. Well, maybe better. Well, this is also, well, if this is also true in this generic situation, if well, just here, okay, we have this form of the potential, and if we just look at this relation, well, when a is equal to 0, then we have that this goes like well, the quotient goes like omega r, which is negative. Okay, so, well, this corresponds to an expansion, which is, but, well, a retarded expansion, or, well, in this case, the radiation dominated regime, which is close to the original singularity, well, the scale factor being 0, then we would have something of this kind, of this sort. Okay, and in between, well, we will have to solve the equations explicitly. Okay, well, the differential equation it cannot be solved analytically, but it can be solved numerically, and of course we can compute for any value of the scale factor, or for any value of the Hubble parameter, we can compute which cosmological time it corresponds to. Okay. Right. So yeah. So that's what we have. In fact, we can solve the cosmological equations in the asymptotic regimes which we have discussed. So well, just remember the cosmological equations. Well, the original cosmological equations, not the scale ones which we obtain. So just remember these two equations. Okay. And well, the thing is that if we impose an equation of state for the matter of this form, well, equation of state, by equation of state I mean a relation between the pressure and the density. So we impose this equation of state, where here gamma is a constant. Okay. Well, if we do that, well, it turns out that we can solve these these differential equations and obtain the explicit value of the scale factor. Okay. Well, I'm not going to do these computations in detail. I'm just going to hint how this is done. It's just that you have to eliminate the pressure from these equations by means of this relation, and so you get that this is just then okay, and then well, this first equation can be easily integrated. Just well, you can just get a value for the for rho in terms of the scale factor. This is standard integration. Just going to keep using the same name for the integration constant. And then, well, as we did when we studied the matter dominate or energy or radiation dominate universes, we just express this integration constant in terms of the present day density and scale factor. Okay, just going to. So this is just okay. So okay. So just replace this here, and then we get okay, and so we insert this value here. We replace the density in this other equation, and in the end we are left with a differential equation for the scale factor, which which can be actually integrated. I'm not going to do the complete computation. I'm just going to present you the result, okay? And this is the result. Okay, where here this small lambda is just the cosmological constant divided by the present day matter density. Okay, right. So that's what we get. The thing now is that, well, we can just particularize this for different values of the constant gamma. Well, you just see from here that when gamma is well, just gamma is 1/3. This corresponds to the radiation, and then when gamma is equal to 1, this is well, this is the case in which rho is equal to p is equal to minus lambda, and this is the, well, if we regard the cosmological constant as a matter term in the Einstein equations, then this corresponds to the dark energy. Okay, so what this means is that in these asymptotic regimes which we discussed, it's possible to obtain the explicit form for the scale factor, okay, by just doing these replacements here. And so, well, this is what I am going to do. And, well, the result is as follows. Well, and well, in the case of the radiation, well, cosmological time is close to 0, so we can just take that this quantity is small, and so it means that we can just approximate this expression and just write okay, and so this is for radiation, and let me just put this this side, just to make clear that we are doing an approximation. Okay, and then for the case of dark energy, what we have now is that scale factor is this. Sorry, this is no. Okay, and then, well, in this case, we can just make also a further approximation if we take that, we realize that cosmological time is large, and so, well, it's just a matter of expanding this hyperbolic sign, and what we get is that scale factor can be written in the following form. Okay, so if you just look at the form of these scale factors, then you see that they sorry, I just I just forgot to write this in the proper way. It's 1/4. Okay, after doing the approximation. So if you look at the form of these scale factors, then you realize that their form matches the asymptotic behavior which we have already obtained by means of a qualitative analysis. Okay, so in this model, the asymptotic regime can be well understood. Well, it's well understood. Okay, so now, well, the point. Well, we must now bear in mind the hypothesis which we did at the beginning to obtain the ΛCDM model, which is just remember this hypothesis. Which is that the matter is cold. Which is the same as saying that the matter is non-relativistic. Okay, well, we did this hypothesis, but well, of course, matter which we see around us does satisfy this hypothesis, but the question now is where this hypothesis is satisfied at all epochs in the evolution of the universe. Okay, well, if we look at the asymptotic regimes, okay, which we have now studied, well, it's clear that well, in this regime, in the regime in which dark energy dominates, well, in that regime, we can expect that the hypothesis will be satisfied. Well, actually, we find ourselves in the present time in this regime. So it means that universe is expanding accelerated, is expanding. Uh, Universe undergoes an accelerated expansion, which we have already explicitly computed when we look at the scale factor. Okay, so it's reasonable that matter and radiation will not interact because they are being pulled apart by the expansion of the universe. Okay. Well, perhaps this will be understood better when we study the Penrose, the global causal structure of the universe. But the thing is that well, if we have an accelerated expansion of the universe, then it means that observers are the distance, the geometric distance between observers is increasing exponentially, and then interaction between different kinds of different components of the universe will be difficult. And so it's reasonable to expect that interaction between radiation and matter will not hold in this, will not happen in this regime. However, in this other regime, well, by definition, radiation is dominating. And well, radiation, well, we modeled radiation by means of an equation of a state which corresponds to relativistic matter. And so what this means is that relativistic matter is matter whose components are moving close to the speed of light, and so is highly energetic matter. And then we can expect that this matter will interact with other components of the universe. So the bottom line is that if we have a universe in which radiation, which high energy, in which a high energy component is dominating the dynamics, then we can just expect that the universe, the interaction between this high energetic part of the universe and its other components of the universe will take place. Well, also we can just think of it because, well, if we look at, well, if the cosmological time approaches zero, then, well, as we know, it means that distances between objects in the universe is reduced, and so the interaction between the objects of the universe will likely happen. Okay, so what this means is that in this when we are in this regime, we expect that an interaction between radiation and matter will happen, and so it means that matter will no longer be cold, and so it means that the main hypothesis for our model will not be true, and so the dynamics which we have discussed here, close to the singularity, it's well, we cannot expect that these dynamics will correspond to the dynamics of the universe. Well, I am going to elaborate further on this idea when we discuss the global causal structure of the universe, but for now, let me just say that if it is true that matter and radiation were interacting in this time, and they no longer interact when we are at this other time, then at some point matter and radiation decouple. Okay, so let me just take this picture, put it down here. So Okay, so what this means is that, okay, in this part, okay, so, and just for this reason, we don't really, well, this model, well, the dynamics which we have obtained with the lambda CDM model might not be valid in this region. But one thing which, well, if it's really true that matter is not cold in this region, and matter and radiation are interacting, and since here matter and radiation no longer interact, okay, so since, as we have discussed here, matter is cold, so it means that at some point in the history of the universe, the interaction of matter and radiation had to stop. Okay, let us just, for example, I don't know, here there is some time which okay, some time, and so from this time on, we can accept the dynamical equations of the universe obtained through the lambda CDM model as a good approximation to the dynamics of the universe. Okay, so the thing is that the radiation which up to this point was interacting with the matter has to be still around. Okay, so this radiation has to be a contribution to the radiation part of the universe. Okay, which we include in the lambda CDM dynamics, and so it must be detectable. But well, if we remember the discussion which we did when we spoke about the redshift, we can just think that, well, if we just remember this discussion, just remember that we have an emitter, okay, and then an observer, okay, and then, well, if the emitter emits radiation towards the observer, the expansion of the universe makes that the received radiation is redshifted. Okay, so if this radiation is the radiation which was in equilibrium, which was interacting with matter during this epoch, then it turns out that well, the radiation which this radiation coming from this epoch which we receive now has to be redshifted. Okay, so there has to, if all this is true, I mean, if matter here is not cold, then the conclusion is that there must be some radiation radiation background in the universe which comes from which comes from which was interacting with matter in this epoch and is no longer interacting with matter. Okay. Well, the thing is that this radiation has been observed, and it's the so-called cosmic microwave background. Okay. Well, so the existence of this cosmic microwave background is a proof that matter and radiation were interacting at an early epoch of the universe, and so it means that we cannot expect that the universe is described with the dynamics of the ΛCDM model when we are close to the uh, uh, t equals 0 time, or when the scale factor is small. Well, okay, what are the implications of this? Well, the implications of this are the following. Well, the first point is that, well, if we just remember at how we obtain these dynamics, well, we just started from this potential. Well, it means that we no longer know for sure what the form of this potential is going to be when big A is close to 0. So conclusion is that, well, since we don't really know the form of this potential here, then this conclusion which we obtain might not be valid. So well, it's in principle not clear whether big A will become 0 or what is going to happen. Okay, so this is one thing. Yeah. So the thing is that well, this is one thing, and the other thing is, of course, that well, this was obtained under the assumption of the dynamics of the ΛCDM. So it's not clear that when we are getting to when the scale factor is small, when the cosmological time is going to 0, then the scale factor will be approximated by this expression. Okay. So we have to be careful about what happens when we are close to the when we are close to the so-called origin of the universe. Okay. So ΛCDM model doesn't really give us an answer about that. And okay, then if the ΛCDM model doesn't give us the answer, what gives us an answer? Or, well, the answer mainly comes through the study of the cosmic microwave background. Okay, well, right. In this lecture, I'm not going to enter into the details about the physical properties of the cosmic microwave background, although it's presently is a very active topic of research. What I'm going to do in this lecture is to mention one property of the cosmic microwave background, which gives us a hint about what might be happening at the origin of the universe. And the property is that well, if one looks at the cosmic microwave background, well, we are the radiation of the cosmic microwave background is coming to us from every region of the sky. Okay. And well, if we study the radiation from different regions of the sky, what we observe is that this is an isotropic radiation. It's okay. It's roughly isotropic. Well, if we look at it over large scales, over large enough regions of the sky, we can say that the CMB is isotropic. Okay. Well, in this lecture, well, of course, it's isotropic when we look, as I'm saying, at large enough scales. But of course, if we look at small scales, then it has an anisotropism. But well, for this, well, of course, this anisotropies give also information, but in this lecture, I'm not going to say anything about them. What I'm going to do in this lecture is study the consequences with this isotropy of the CMV has about our knowledge of the dynamics of the universe when the scale factor is small, when we are close to the so-called Big Bang or initial singularity. Okay, right. Well, and how am I going to do that? Well, I will do that by means of studying the global causal structure of the universe, which will be done by means of the study of its Penrose diagram. Okay. Well, okay. Well, the idea is that well, the fact that the CMB is isotropy will tell us something about the global causal structure of the universe when we are close when the scale factor is small, when we are close to the so-called original singularity, and this information will be relevant for the study of the primitive universe. Okay, but for that I need to compute the Penrose diagram of the universe. Well, just remember that if you go to the lecture in which I discussed Penrose diagrams, well, if you remember if you look at that lecture, just remember the Penrose diagrams can be computed for spherically symmetric solutions, and well, if you just remember the line element of the universe, then we have that this line element corresponds to a spherical symmetric solution. Okay, so it's possible to compute the just by, well, we have this spherical symmetric part. So what I'm going to do now is I'm going to compute the Penrose diagram of the universe. Okay, when this varies according to the dynamics of the ΛCDM model, and then once, well, of course, the Penrose diagram will give us information about the global causal structure of the universe, the way in which I explained in the lecture about Penrose diagrams, and then we will see whether this causal structure is compatible with this property. And if it's not compatible, then we will see what can be done to make it compatible. Okay, right. So this is what I'm going to do next. In the lambda CDM model, the curvature parameter is taken to be 0. So if we just do that here, what we get is it's in the notation. Okay, where of course this corresponds to flat Euclidean space, and so well we can just write this in an explicitly conformally flat way if we do that change, the following change. We introduce a new variable capital T, so this gives okay. So yeah, so this is what we have, and now well it's just now following the standard procedure to construct the Penrose diagram and take this Lorentzian part, the metric, the spherical symmetric metric, and so what we do now is, well, of course here now small t has to be considered as a function of big T. Just going to write here. Okay, so now we have just to concentrate on this Lorentzian part, which I'm going to write here. Okay, here and then we do the standard coordinate transformation which one does when computing the Penrose diagram. Okay, so I'm just have a look at the lecture about the Penrose diagrams. I'm just going to write here the transformation. Just remember what we are doing is computing the conformal compactification of this two-dimensional metric. Okay. Okay. And so, as we studied when in the lecture about the Penrose diagrams, after this transformation, the metric takes the following form. Okay, so I'm just going to write the result. Where here this a tilde t is just a okay. Okay, so this is the this is just the conformal compactification of this metric, And well, now it's just the Penrose diagram is given by studying the zeros of this function. Well, we have to find the region which is bounded by the zero set of this function, which is just the inverse of the conformal factor. Okay. And well, the zeros of the numerator are standard. What already started in the lecture about Penrose diagrams. So I'm just going to give the result here. Okay, so so this is the the space in the new coordinates, and well, this represents big R equal to 0. This part here, and here, well, these lines correspond to the zeros of the numerator. Okay, so what we need to know is what we need to do now is to study how this triangle here is restricted when we study this function. Well, the first thing is just just remember that we have to consider only the part in which corresponds to the scale factor being positive, which means that this other function has also to be positive. So we need to find which part of this triangle corresponds to this region, and of course we have to find the explicit form of this function and see and find additional points on here on this triangle which make this function vanish. Okay, and well, of course, this is all model. To do that, we need to know the explicit form of this function, and of course, this will depend on the explicit cosmological model which we are studying. Well, in our case, it's the ΛCDM model, but well, we don't have the explicit form of this function for the ΛCDM model at all values of the cosmological time. We only know those values for the asymptotic regimes, which we discussed before, for the case in which dark energy dominates and for the case in which radiation dominates. So what we are going to do is we are going to obtain the diagrams for each of these situations, and then we will patch those diagrams together and see and in that sense, in that way, we will get an idea of how the Penrose diagram of the universe looks like. Okay, so this is what we are going to do. So well, let us start by the radiation dominated era. In that case, we just obtain that the scale factor takes this form in terms of the present day scale factor and the present day matter density. Okay, so well, we just have to first obtain do this do this change. Okay, well, so this is well, this relation can be obtained if we do if if we do an integral, okay, so here just have to use this expression to obtain big T in terms of small t, okay. And well, just do a computation. Well, not going to do the details, just give the result. Well, I'm just going to, if you do the integral and invert what you get, then you obtain the following relation for between small t and big T. And so, well, you just have to input, replace this here, and so what you get is that just after doing some elementary manipulations, which I encourage you to do, what you get is that okay, so okay, so yeah, of course, right, so here, well, well, now it's from this expression we see that this is 0 only when big T is equal to 0, which if we just look at the coordinate transformation which we used to in the conformal compactification, we realize that this corresponds to sine u being 0, and so this is u equal to 0 inside this triangle. Okay, this corresponds to this axis, right? So we are only forced to, we can only consider one part of this triangle. Okay, right. So this is one thing, and well, in this case, if we just if we replace the value which we obtain of a tilde in this expression, then we see that the only points in which this function vanishes are just these lines which were already considered, which correspond to the zeros of the numerator. Okay, so what this tells us is that in the radiation dominated era, the Penrose diagram of the universe is either one of these triangles. Well, typically we are considering, well, given our choice of time orientation, we consider that the singularity is in the past, and so we will pick this upper triangle because our time orientation goes according to this arrow. Okay, so this is this triangle would correspond to the Penrose diagram of universe, of radiation dominated universe. Well, of course, radiation dominated universe is only valid for a part of the history of the universe, so we cannot say yet that this upper part of the diagram will correspond to the Penrose diagram of the universe. To continue to do that, to find the Penrose diagram of the universe, we have to consider what happens in the other asymptotic regime, which is the dark energy dominated era. So just going to and so what we have to do is essentially the same what we have done. So now just remember that the expression of the scale factor is we obtained before is this one. Okay, so now again we have to do the integral to obtain big T in terms of small t. Okay, now I have to choose some reference time in which we think that the universe is energy dominated era. For example, if we assume that the present cosmological time is already in this regime, then I can take this time as the integration limit, and then the other limit is just any other time in the future. And so what we have to do is this integral and well, I'm just going again to show you the result, and just going to give small t in terms of big T. Again, I encourage you to check the computations. Okay, so this is what okay, and therefore we just have to input this relation here to obtain the function a tilde, and this is the result. Okay. Okay. So this is what we get. Well, now this expression implies that this function cannot be zero. Okay. So we don't need to worry about the restriction of this function being zero. But what happens now is that when we substitute this function into the into this other function, then we see that in addition to the zeros of these cosines, which we already represented in the diagram, we need to worry about the zeros of this expression. Okay, we need to study now the zeros of this expression. Okay. This is just and well, just remember that big T is given by this relation. Okay, so we need to represent this set into the diagram. Okay, we have to for these values of the constants. Okay, so we need to see what this search corresponds to. Well, you can do that with any computer program which does graphical representations, and I'm going to give you the result. The result is this. Okay, so this red line corresponds to I'm just going, sorry, we just call this well, actually this corresponds to the value in which the scale factor is infinite. Okay. Yeah, you can just you can just see this. Well, you can see this just by looking at this expression. Okay, when this big T when this is 0, then of course this goes to infinite, and if this a tilde goes to infinite, just by its definition implies that the scale of the original scale factor goes to infinite. So well, this part of this set of the diagram corresponds to the infinite, to the future infinite of the universe, actually. Okay, so this is so in this case, when we studied the radiation dominated regime, this corresponded to the scale factor being 0, and now this corresponds to in the radiation, the dark energy dominated regime. This boundary corresponds to equal infinite. So the universe is in between these two sets. Okay, so this is the universe, and of course, well, these are the asymptotic regimes. So we expect this to be valid only in the asymptotic regimes. In this region, which is here in between, the dynamics, well, we have to solve the equations to find the dynamics, but we expect that this is an approximation of the Penrose diagram of the complete universe. Okay, well, I'm going to draw here a better picture of this diagram. Okay, so here it is. This is just a zoom of the region in which I just discussed. Okay, and well, this is what I said, and these blue lines correspond to spatial sections of the universe. Well, these are the comoving hypersurfaces. Okay. Okay, and now, well, in this case, this is big R. Okay, and now, well, what does this diagram tells us? Well, it tells us something important in relation to this region, which is close to the singularity, which is the following. Okay, so if we look at this region, well, let's just erase these points for a second. Okay, so well, suppose that we have an observer here in one of the. Suppose that this sigma naught is the universe at the present time. Okay, and so suppose that this point is us. Okay, now, and then well, I'm just going to draw the point some here. Okay, so suppose that suppose that this point is us now in the present time, and well, I explained that we are receiving radiation from the time in which radiation and matter were in equilibrium, and then well, this time is close to here to the singularity, which is the epoch in which the radiation dominates, and so this radiation, which forms the cosmic microwave background, comes to us from all regions of the sky. So these regions or these points of the sky, well, will correspond to different parts of the universe. So suppose that we receive radiation from a point A, and we receive radiation from a point B. Okay, so well, just remember that in a Penrose diagram, light rays go are straight lines which have a slope of 45 degrees. Okay, so I'm just drawing the light rays which we get from 2 points A and B, which are close to the singularity. Well, I have drawn them in the singularity in the picture, but you should understand them as close to the singularity rather than in the singularity itself. And then, okay, this radiation coming from points A and B will be measured in the cosmic microwave background. The thing is that these points A and B are causally disconnected. It means that, well, if you look at them in the diagram, there is no way that they can exchange information, because they cannot be connected by a causal path. This is very clearly seen in the diagram, because causal paths have to have a slope which is less than 45 degrees, or less or equal than 45 degrees, and here any curve which connects the points A and B have a slope which is greater than 45 degrees. So information could have to travel faster than light, and that's not possible. So information between A and B cannot be exchanged. So it means that radiation coming from A and B, well, the radiation in the cosmic microwave background from A and B should appear different, okay? However, I said before that cosmic microwave background is isotropic. The radiation of the CMB is isotropic. Okay, so what this means is that this diagram, at least in this as in close to the singularity, cannot explain why the CMB radiation is isotropic. Okay, so this is an indication that this is happening because, as I said before, the hypothesis that the matter is cold doesn't hold when we are close to this region of. Okay, so of course this is yet this is the isotropy of the CMB is telling us that well, I already mentioned this when I spoke about the CMB, but this is shown again when we study when we compute the Penrose diagram of the universe, assuming the cold dark matter hypothesis. Okay, so well, the question is, well, is there any way to fix this? Well, of course, to fix that, one has to drop the hypothesis of cold dark matter when we are close to the singularity, and this leads us to a different dynamics of the universe. What is that dynamics? Well, my answer is I don't know. There are many people doing research about this new dynamics, but what we can do is we can just guess what the Penrose diagram of the universe looks like, in order that the new diagram is compatible with this property. Okay, and what is this new diagram? Well, I'm just going to okay. I'm just going to show you what a diagram in which this isotropy of the cosmic microwave background can be explained. Well, here it is, the diagram. Well, well, doesn't quite fit. I will have to do a bit of, well, okay, maybe. Okay, well, it doesn't quite fit in the board, but I think that you will be able to understand the main ideas. Okay. Well, now the upper part of the diagram is the same as the upper part of the previous diagram. Well, this because it corresponds to the region in which dark energy dominates. What is different now is the lower part, okay? Well, in the previous diagram, we saw that essentially the problem was that singularity, the A equals 0 region corresponds to a space like a hypersurface in the diagram. So this fact implies that A and B cannot exchange information, and that led us to a cosmic microwave background, which in principle is not isotropic. Now we have changed that. We have put here this region, which is supposed to correspond to the initial state of the universe, and then, well, if we do the same now, this point set is us again at the present time. Then, well, the point is that well, A and B emit radiation, and then the thing is that the radiation which we get from A and B, well, we get radiation from A and B, but now A and B are causally connected. They have had the chance of exchanging information, and so in this fashion we can expect that the radiation which comes from A and B to us is similar, because there has been some interaction between A and B. Okay, so if the Penrose diagram of the universe looks like this, then we can expect that this is compatible with the isotropy of the cosmic microwave background. Okay. Right. So in this case, we can take this diagram as an approximation of the dynamics of the universe. The question is, well, what kind of dynamics creates this diagram when the universe is close to its initial state? Well, I am not going to say, well, this is an active topic of research. I'm not going to expand into this in this lecture. I'm just going to one of the most researched mechanisms to obtain this is the inflation, but and I'm not going to say anything about inflation in this lecture. What I'm going to mention is that well, I have in this lecture I have avoided the word Big Bang, because, well, most of the cosmology textbooks speak about the Big Bang as the initial singularity or initial time of the universe, the time at which the universe was created, or initial singularity in which all physical laws break down. I have avoided this word because, well, the fact is that we don't really know what is going on here. As I'm saying, this is an active topic of research, and, well, it might turn out that there's not even a singularity here. That well, this is another well, that this is a kind of a boundary which leads to another universe. So we don't know. It's being researched, and, well, there are many hypotheses as to what happens when we are close to this region. But as for now, we don't really know whether this is a singularity or not. So that's the reason why I avoided the standard terminology of Big Bang in this lecture. Okay, right. And another thing which I would like to mention is, well, we don't know what is going on here, but, well, we have some idea of what is happening now and what is going to happen in the future. Well, if the universe is dark energy dominated, and another thing which happens is that the appearance of cosmological horizons. Okay, so just to understand this, suppose that P and Q are observers in the future. Okay, and then, well, the thing is that this region here is the set of the region of the universe which the P can influence, because, well, it's these are light rays, and so these are points which can be reached by P, through a causal curve. And the thing is that the fact that the conformal boundary here is space-like, then it implies that the information, the set of the region which the region of the universe which P can influence and the region of the universe which Q can influence are completely separated. Okay, so what this means is that P and Q will never be able to notice each other or to exchange any kind of information, just due to this region. So this boundary here is a so-called cosmological horizon. Okay, and, well, it's just that the part of the universe which is outside from which is on the other side of this horizon cannot be influenced by P in any way, and so P will never know about that part of the universe. Well, what is happening? Well, just remember that in this regime, the scale factor is an exponential in the cosmological time. So what is happening here is that the cosmological expansion is so strong that at some point the velocity which P will see objects separate from him will be greater than the speed of light, and so these objects will disappear behind an horizon, which in this case is a cosmological horizon. Okay, and again, this is a consequence that this is a space-like curve in this picture, and it's well, and this in turn is a consequence that dark energy is dominating the dynamics of the universe. So dark energy is pulling objects in the universe apart, and at some point it does it so fast that objects are separating with respect to an observer at a speed greater than the speed of light, and so the observer can no longer see any information from these objects. Okay, right. Okay, so right, this is all I wanted to see in this lecture. I hope you enjoyed it, and, well, thank you very much for your attention. Goodbye.